Hamming Medal for contributions to information transmission, and the 2015 Claude E. Shannon Award. So with that, I would like to invite Rob, as we say him, to deliver this talk on waveforms for 6G communications.
All right, thank you very much. Thank you very much for the kind introduction. I'll try and talk for like 40 minutes, and maybe leave a little time at the end for questions. I should say at the beginning that I'll be talking about joint work with Ronnie Hadani from Cohere, and with Professor Mohammed here at IIT Delhi, and Professor Chokalingam from Indian Institute of Science in Bangalore. And just in case you look at the talk and you feel cheated because there's not enough math in the talk, and you're wondering where did he hide the math? The math is hidden in this magazine paper that we all wrote together. We're actually quite proud of this paper. It took us, there are actually 2 papers, and it took us over a year to write them. And we think we did a good job. So we encourage you to sample the magazine papers and see if you agree. All right. What I'm going to do is I'm going to start by talking about innovation in standards. And so here, there's a lovely quote from Orwell. Orwell says, "Every generation imagines itself to be more intelligent than the one that came before it, and wiser than the one that came after it." It's a great quote. And what I've done here is you see the generations marching across the slide every 10 years. I've tried to characterize the different generations, to characterize what their primary application was, and to give you the acronyms associated with the technology. And what I'm going to do in the talk is I'm going to say, look, things change in wireless. And they change for a mixture of 2 reasons. One reason they change is that the world changes. And the other reason they change is that you can do something new. And we'll start with the world. So these are what I've called market forces. And so here, I'm going to go back to the beginnings of wireless. So this is in the 40s and 50s. The US was terrified of the Russians because the Russians knew how to communicate. They knew the mathematics of communication, and we really didn't. And there was a project that was started by the Army Signal Corps. They asked MIT to develop a communication system that was robust to noise and deliberate jamming. They were inspired in part by the Berlin airlift. And this project was called Project Lincoln, and it led to the creation of Lincoln Labs at MIT. It was centered around the idea of using noise-like waveforms to communicate. So NOMAC is noise modulation and coding. So you would have a band, you would spread your signal across the band, and one signal will be a 0, one signal will be a 1, and you sent it out into the world. And this was research done at MIT in the 1950s. It was only actually declassified in around 1961. But seminal paper is this paper by Price and Green. And the big theoretical breakthrough is the development of the rake receiver. And the rake receiver was necessary because the US did a transcontinental field test of NOMAC. So they took they transmitted signals, they bounced them off the ionosphere, they collected them at the other end, and they discovered that their system didn't work very well. And it didn't work very well because they were just collecting energy from the dominant path. There were 20 to 30 paths that they weren't collecting energy from. So they weren't taking into consideration these weaker paths. And the solution was the rake receiver, which in a sense was to take the signal you got and make many copies of it, delayed by a certain amount of time, and use the collection of copies to detect. So this is said very nicely by Price and Green. They say selective fading is opposed by detecting the echo signals, that's the individual paths, using a correlation method and then adding them algebraically with the same sign rather than vectorially. They didn't want the signals to cancel out. And intersymbol interference is dealt with by reinserting different delays into various detected echoes so that they fall into step again. It's a very nice description. And it connects with India because Thomas Kailath started his PhD, started his master's studies at MIT in 1957. And these were studies around estimating channels. How much bandwidth did you need? How much time did you need to detect a signal? And so Kailath in his thesis developed the conjecture that B, the bandwidth, and T, the time, BT had to be less than 1. And on the NOMAC receiver, they observed that when BT was bigger than 1, bad things happened. So the rake receiver was one of the key innovations in 2G. So this is CDMA. 3 and 4G, the big innovation was spatial diversity. And it was a challenge that was driven by a world that needed to get more data. So how did you satisfy demand for high-speed data? And Paul Roche, who was mentioned this morning, was one of the key figures. Has a 1992 patent on spatial diversity. It's actually kind of base station diversity. But his demonstration was that multiple antennas dispersed in space dramatically improve the capacity of a wireless system. Nambi Seshadri and I at AT&T developed space-time coding, where the aim was to improve the data rate, the reliability of communication over fading channels using multiple transmit antennas. And so spatial diversity was the big thing in 3G and 4G systems. It made high-speed data to many users possible. Now, the really big innovation in 4G was Rajiv Laroya. And I'm actually very proud of having the sense to hire Rajiv Laroya at Bell Labs. Actually, I have to say that I actually had a position in applied mathematics, and I gave that position to Aaron Weiner on one condition, that he used it to hire Rajiv. Because I had looked at Rajiv's thesis, and what I concluded after looking at his thesis was that I wasn't sure that his advisor could have written it. And so I thought, you're better than your advisor. And I was exactly right. Anyway, Rajiv had this, Rajiv and I worked on voice-band modems for a little bit, and then he started working on wireless. And he recognized that the paradigm at that time, which was circuit switching, wasn't going to accommodate direct wireless connection to the internet. When people use the internet, sometimes they weren't doing anything at all, and sometimes they wanted a lot of data, and they kind of bursted between the two. And so you needed a MAC layer that could provide Airlink resources basically on demand. And so the key patent that Rajiv has is splitting users into 3 states. There's an active state, there's a quiescent state, and there's an about to do something state. And before, users were either doing something or they were completely out of the picture. And this vision that enabled a larger number of users was exactly the right thing for the wireless internet. Rajiv is I mean, there are many people who have great theoretical insights. Rajiv actually founded a company, Flarion, to commercialize his vision. One of the interesting things for me watching Rajiv was the way he assembled a team. Because we had worked together on voice band modems, and so he had toured all of these places like Rockwell, and he had talked to the key development engineers. And he knew exactly who he wanted on his team. And he recruited a fantastic team at Flarion. The system was very successful. It was beautifully engineered. The company was acquired by Qualcomm. And ever since, Qualcomm has been making a very nice living off of OFDMA. And so we all feel, I was on the technical advisory board of Flarion. We all feel very good that Qualcomm's doing so well. Occasionally we feel a little less good. What might be coming next? So this is speculation. Krishna Narayanan is sitting right there. He's one of the people who looked at wireless communications, and he said, you know, today we think of users as data sinks, right? You're a user, you browse the internet, you consume video streaming, bits flow to you. You're a data sink. If in the future we imagine applications like distributed machine learning, that's going to put more pressure on the uplink. Now, we talked this morning about services. When on earth were they going to appear? And, you know, physical layer engineers can't make services appear. So, I mean, services appear because of market forces. But one thing I will say as an engineer is that if you don't have the right architecture that allows the service to appear, then it won't appear. And I think that there's many things that we can do to improve the uplink. Krishna is part of the team that I think inspired this notion of the two-step RATCH, which is part of release 15 of 3GPP. In the beginning on the uplink, they had this really ugly 4-step protocol, which was almost designed to not make services appear. And they've replaced that by a 2-step procedure, which I've kind of given a cartoon of on this page. So there's 2 steps. The first step is where you send a preamble. The preamble is something called a ZF2 sequence. And the challenge is to detect a preamble or multiple preambles in the presence of delay and Doppler. I think Krishna might be giving a talk about how you might do that. Once you've done that, the user uploads data in something called a push frame. And so this traffic is, you want an enormous number of potential users, much more enormous than Rajiv's number. Only a couple of hundred of them will be active at any one time, but you want to be able to accommodate them. And you want to have some kind of slot structure, a little bit like Aloha, where you can make sense of all the people that want to transmit. And so the idea is I send a preamble. The preamble points to where I'm going to send my data, which slots I'm going to send data, and I just send data in those slots. The base station figures it out. Now, we have different users in different spots. They have different channels. Base station has to figure out all of that. And I think Krishna will talk a little bit about this uncoordinated random access. Okay. So these are actual market forces or imagined market forces. Let me now talk a little bit about the opportunity. So what distinguishes 6G from the previous generations is, I think, Doppler, in large part. Here I've made a list of the channels in order of increasing Doppler. So we start off with terrestrial pedestrian channels, where there's basically no Doppler. And then mobile, maybe 300 hertz, millimeter wave, perhaps 3 kilohertz, and so on. And what I would say is today we design wireless systems using mathematical models of the channel. One of the messages of this talk is stop estimating channels. Don't do it. You're not interested in channels. You're interested in the input-output relation. If you can estimate the input-output relation, you don't care about the channel. And actually, there are times when you don't have the bandwidth or the time to estimate the channel. So it's not that you don't care about it, you just can't get to it. But what I'm going to discuss in this talk is that it might be possible to operate model-free. So that's a kind of a machine learning AI type thing. And we know that machine learning and AI has revolutionized all sorts of fields. It's even changed the way mathematicians think about mathematics. I mean, mathematicians used to have this whole hierarchy of Bezoff spaces that measured how continuous a function was, how many times you could differentiate it. They're starting to think of functions in how closely can you approximate them with a neural network. Right? That's a fundamentally different way of looking at the world. This is a 6G picture. It emphasizes AI. I would say that when you think about AI and ML, it's not really about consuming these AI and ML algorithms that have been produced by people like DeepMind or Google, that work off enormous amounts of training data, and they take a while to give you their answer. If you're doing wireless, particularly if you're doing detection and estimation, I give you 14 OFDM symbols, you have to tell me what I transmitted, right? So making AI and machine learning work at the speed of wireless is really the challenge. I would say, actually, I'm going to talk about waveforms. This slide is about, it's not really the waveform, guys. It's really the architecture. And so when I think about OFDM and carrier spacing, what OFDM does with carrier spacing is it tries to avoid inter-carrier interference. If the channel gets too ugly, it'll space the tones further apart. So OFDM is engineered to avoid inter-carrier interference. Okay? Now, a long, long time ago, when you guys had laptops that used magnetic recording, we encoded data on disks. And we spaced the transitions far enough apart so they didn't interfere. And we used a peak detector. It's like OFDM. Now, what happened with data storage was that people wanted more and more data, and they wanted it in a smaller and smaller form factor, so you didn't have a choice. You couldn't space these things far apart. You had to space them close together, and you had to resolve the intersymbol interference.
I am absolutely confident that none of you in the audience has a laptop that has a peak detector. And so OFDM separate inter-symbol interference. OTVS, which is what I'll talk about, is where you embrace inter-symbol interference and then you equalize the data. And I would suggest that the embracing inter-symbol interference is the good solution. All right, so I'm going to give some cartoons about how this works and how machine learning and AI enters. Okay, and so here so this is a cartoon. I explain the cartoon in a little bit. Actually, perhaps I'll go to this. And so here, on the left-hand side of the picture here, you're sending a signal. And on the left-hand side, you have these vertical columns. They correspond to different reflectors. And some of the reflectors are stationary and some of them are moving. What they do is they produce replicas of the signal that you send. Okay? Delay, with replicas with a delay and with a Doppler shift. And the idea is that you send a signal, you get these replicas. But this happens in a consistent way. If I sent another signal, I get the same set of replicas because I have the same set of reflectors. So the idea is that I can send one signal, one pulse, and I can measure the return, and I know what's happening in the whole grid. So this is the acquiring the input-output relation, right? That's what I'm going to do. And so here, I send a pilot. I'll explain this grid in a minute. What I receive is a copy of the channel, which I just read off. I acquire the channel. It's really simple. And then I use what I've acquired to equalize the data. How does this work? So now I'm going to have to wave my hands at the delay Doppler domain. So this is it's very interesting. So we are going, now of course, when you transmit signals, you transmit them in the time domain. But what I'm going to propose is that we design signals in the delay Doppler domain. And here, there are going to be pulses. Mathematically, they're quasi-periodic functions. So when you move up in Doppler, nothing happens. When you move across in delay, phases get added. Let me wave my hands a little bit at how this happens. So you've got the delay Doppler box. So the idea is here you're an engineer. What do you know about your system? You don't know exactly what the delays are. You don't know exactly what the Dopplers are, but you do know an upper bound on your delays. Okay? And you do know an upper bound on your Dopplers because things only move so fast. So you can configure this box, the tau p and the nu p, which give you, that's your Doppler spread and your delay spread. And you configure your box. The product of tau p and nu p we take to be 1, so this is an underspread channel, a doubly dispersive channel. And here, let me tell you how the pulse relates to the time domain waveform. So take the pulse, and it's realized as a pulse train. The little pulses in the train are separated by tau p. That's the delay period. They're modulated by a tone. When you look at the pulse in the box, it's at the point tau 0 and nu 0. Tau 0 gives you the offset of the pulse train. Nu 0 tells you about the tone that's modulating the pulse train. So this is the waveform that we use. Now, if you're a practicing communication engineer and you look at this and you think, okay, fine. By the way, this is a waveform that has one ugly peak to average power ratio, because look at all those peaks, right? That's not, and peak to average power ratio is really important because if you have bad PAPR, it really stresses your amplifiers. You have to work with expensive amplifiers. And so we want to find ways to reduce that PAPR. I'm going to talk a little bit about that. This is the system architecture. I don't expect you to take in all of the box. The important thing mathematically is that these reflectors act on the signal by something called twisted convolution. Now, you shouldn't be afraid of twisted convolution because you're not afraid of convolution because you teach that all the time. So twisted convolution is just like convolution, except it comes with phase factors. So it's like convolution with a twist. And everything acts by twisted convolution. Reflectors act by twisted convolution. The filters that I'm going to talk about act by twisted convolution. The great thing about twisted convolution is that it's associative. Why do you care about a mathematical property like associativity? You care because at the end of the day, you get a relationship between the input and the output, which is just given by convolution. You can acquire that HDD, the effective channel. Once you've acquired it, you can equalize your data. The problem with other sorts of modulations like OFDM is that this relation doesn't hold. They're not predictable in the same way. And why does it matter? Well, what we've done here is so what's this experiment? Model-free versus model-dependent. So we picked a channel out of 3GPP. We pick the vehicular A channel, and we instantiate it in a place where we don't have enough time and bandwidth to measure the channel. So we're trying to make our life really difficult. And we're using our modulation where we just acquire the input-output relation in the way I just described, then we equalize the data. What I'm showing here, the bottom curve is performance given a Gini. The Gini tells you what the channel is. The blue curve that's just above it is model-free, where we just read off the input-output relation and equalize the data. You can see it's very close. So this suggests that model-free works pretty well. The upper blue curve is where we can't estimate the channel, but we try and do it anyway. Doesn't work really well. There's a big gap. The red curves are TDM and FDM. They don't work at all. And this is the picture that you get. Okay? So, and this is explained in the paper, that this way, so here we've organized so that we live in a box that is bounded by the delay spread and the Doppler spread. And if we signal inside of that box, everything's consistent, everything's predictable. Mathematically, what we have is a two-dimensional Gaussian channel. We acquire the two-dimensional Gaussian channel, we equalize the data. Life is good. When we get outside the box into areas like TDM or FDM, things start to go wrong. See, when we're in the middle, in the predictability region, I said that we have these pulses, they're quasi-periodic functions. And in the box, the different replicas, the different purple things there, what is the purple thing here? It's the channel, right? So the channels are not interfering in the different boxes. There's no intersymbol interference. And that's why we get predictability. When we move towards the TDM end, we start to get aliasing in Doppler. So when we're in that dark purple region, we feel two replicas. And if we were at a different part there, if we had green channels and they're met in a dark green part, we couldn't predict what was happening in the dark green part from what happens in the purple part. It's like we have equations in two unknowns, and we have one set of coefficients in purple, and we have one set of coefficients in green, and they're linearly independent, and we can't predict the outcome of the one from the other. Okay? And so if you're an electrical engineer, this should be a familiar picture because you teach signals and systems, you know all about aliasing. This is exactly what you know, except we're doing it in 2 dimensions. So the idea is that time selectivity and frequency selectivity, these are just things that you do to yourself because you haven't configured your channel properly. So if you have aliasing in Doppler, you get time selectivity. If you have aliasing in delay, you get frequency selectivity. But you can avoid selectivity by operating in this crystalline regime. Now I'm looking at my watch because I don't want to go past 3, so I'm going to cut some things here. I'm going to I want to talk a little bit about integrated sensing and communication. And here, when I talk about sensing, I'm talking about sensing the I/O relation. Okay? I'm not talking about vehicular radar. I'm interested in vehicular radar, but this is not a talk about vehicular radar. And so the idea here is, let's take one of these point pulsones, and let's try and put data and pilot in the same frame. If I do that, then I have to create a guard region around my pilot, because otherwise I'm going to acquire the channel in the guard region, and I can't pollute it with data symbols. Okay? So the idea is I'm going to read off the channel from the guard band. Once I read off the channel, I know which part of my received signal comes from the pilot. I can estimate that, I can subtract it off, and then I can recover the data. So that's how I proceed. This is my remark about peak to average power ratio. This is not a pretty peak to average power ratio. And what I'm now going to just give you a taste of is how you can design. This is really a reimagining of CDMA. What did we not like about CDMA? We love the fact that it was spread across the band. We love the fact that maybe it was more secure. We hated the fact that we couldn't equalize it, that there was no relation between the sequences we're using to spread the data and how we might equalize it. And we can solve this problem. So the idea here is that we're going to replace this peaky waveform. So here I've given its time domain and its delay Doppler domain representations. And we're going to replace it by a noise-like waveform. And the energy is spread equally across all the modes of the channel. So if we have energy 1, the energy in each of these little bins is 1 over mn, where we have m things in delay and n things in Doppler. I don't think I'm going to do that. So what we will have here is what in a sense we've done mathematically. So if you're curious mathematically, we have pilot symbols and we have data symbols. And we've actually created pilot and data so that they're mutually unbiased. One looks like noise to the other. So that when we're estimating channels, we're getting noise-like interference from the data, and conversely. So here, I'm going to skip the mathematical details of exactly how we do this. But it's the same idea. We have the point data and we have the spread pilot. They coexisting in the same frame. When people think about integrated sensing and communication, they often write papers about how we have these two functions and we have these resources and we're going to divide our resources between the two functions and then we're going to try and optimize the trade-off. I don't want to do that. I want them all to coexist in the same space. I don't want to give up anything. And my point here is that we can do that. This is some of the math that's buried. And here, just as a final remark, we do turbo signal processing at the end. So we send our spread pilot. We get an estimate of the channel. We can figure out what are, in the received signal, what came from the pilot. We subtract it. We back out the data. And then we just do a turbo step. We've estimated the data. We can now estimate, and we had an estimate of the channel. We can back out the contribution of the data to the received signal, and we can re-estimate the pilot. So that's a turbo step. We do 5 turbo steps. I think 2 isn't quite enough, but 5 certainly is. And we can get really good bit error rate performance. This is uncoded for QAM. The things that we do get to play with, we have to think about how much energy do we put in the pilot, how much do we put in the data. So that's a parameter to trade off. Conclusions. I'm not going to talk about passive radar. We've got this, and maybe I'll just conclude with this. Do we need a new waveform? Ronnie Hedoni was giving a talk at University of Texas to Jeff Andrews, who I admire a lot. He's really a great wireless researcher. And before he went in, I said, Ronnie, you should take a look at Jeff's citations over the last 5 years. And when you do that, they sort of go down like this. So, and that's my way of saying, you know, interest in OFDM and classical solutions has not been growing dramatically. But we wrote a paper in 2017. Anton is here. He's one of the authors. And this curve has the opposite characteristic. Last time I looked, it had over 400 this year. And it's growing at about 25% a year. And so there's worldwide theoretical interest in delayed Doppler signal processing, in OTFS. This was the picture of which countries. India is well represented here. It's number 3. And there's theoretical developments, but there's also over-the-air implementations. There was, in April of this year, Vivavi Solutions had a video demo of OTFS that got a lot of play. We're working with people at the Air Force Research Lab. I'm not here to advocate for terahertz as a 6G thing. It is, however, a really interesting physics experiment, and Venkatesh, who was Saif's graduate student and who is now a postdoc with me at Duke, has been working with Claire Parisi. He's basically been transferring our OTFS code to Air Force Research Lab, and Claire is putting it into practice. So we're really excited about this development. We have other over-the-air projects going on, and we're happy to work with all sorts of people who would like to work with us. Well, it's 3 o'clock. Happy to entertain questions. Yeah.
Yes, I'll just start off. So the spectral efficiency of all these waveforms, is there anything to gain in terms of spectral efficiency here?
Yes. And let me give you a couple of things. One is we're acquiring this input-output relation, okay? What we are essentially doing is acquiring the reflectors, okay? We're acquiring the reflectors. And how quickly do reflectors change, right? They don't change very fast, right? I mean, they do change. But we've bought you some time for signal processing, right? If we're doing something like scheduling, we're going to use that I/O relation to make a map of where you are, and we're going to think about how we can give you resources. And whatever decision we're going to come to is going to be good for longer. And so we're going to be better at making use of the bandwidth. So that's going to improve spectral efficiency. And I'm looking at Ray because this is his product. And and so I'll leave it to him to say what sort of improvements he can get. But they're significant enough to attract interest from vendors. So that's the other thing is, I mean, so we're kind of communication nerds. So we get excited about nerd things. And you can make really interesting filters, right? So if you're doing OFDM, you can do sinc filters, or you can do root raised cosine filters. That's fine. Here, in 2 dimensions, you can make factorizable filters. So you can make Gaussian filters that roll off really quickly. And so we think that that's going to be an advantage. So we're excited about that. Yeah, go ahead.
Ask the question more generally, are there areas, general areas of benefit to driving into an OTFS domain? I would say, A, spectral efficiency, yes. It is somewhat dependent on the complexity of the channel because OFDM has enough solid attributes that in a non-complex channel, the benefits of OTFS are X. As the channel complexity goes up, the benefits start to become even larger and larger. So you have to consider there'd be a range of spectral efficiency, perhaps starting as low as 20% and probably exceeding 100% in extremely complex channels. That's how I would generally characterize it. And I'm trying to be straight about this because I'm very passionate about it, but I don't want this to be a commercial for our company, right? Because this is a much broader discussion about 6G. But beyond spectral efficiency, which by the way, in today's dollars, if you aggregated all the money spent to date around the globe, is about $1 trillion. So if you can make a 20% improvement on $1 trillion of assets, that's a big deal. And if it's 100%, it's a really big deal. Okay? So that's spectral efficiency. But that's not going to be the only currency that we trade on in 6G. There's going to be power. Many of the things that Rob talked about were the ability to read directly off a channel with a single pilot or maybe perhaps a few pilots as opposed to orders of magnitude more pilots. And it turns out, it looks like, that the power consumption of base stations is very highly correlated to the pilot power. So to the extent that you can tame the number of pilots, you can tame the power requirements of a base station in the entire RF chain, and you can make a significant dent on power consumption. And then, of course, the air conditioning power consumption is a function of the power generated by the rest of the base station. So you end up making a massive dent on power, which I believe right after spectral efficiency, you're going to have power, right? Then there's architectural issues, like the fact that OTFS allows you to buy time. because you can predict into the future. And we're going to be able to explore whether you can then architect the control plane to move a node in to the network at the first data center as opposed to staying on the edge, where the only thing it sees is an individual base station's visibility. And of course, in a cellular system, half the system noise comes from within a base station and half the system noise comes between base stations. And if your only architectural visibility is from the actual base station, you're only controlling half the system performance. So I look at this as a directionally good thing. And I'm very, very passionate about it, but I still believe that as long as 6G is open and it allows waveforms to compete on their merits, then if what I'm saying is not true, or if what I'm saying is eclipsed by something else that's even better, good for the industry. But as long as OTFS can become one of multiple modes in 6G, and it can stand on its own 2 feet, and that some of these attributes are proven, it's going to have peaked average power benefits, it's going to have pilot power benefits, it's going to have spectral benefits, it's going to have architectural cloud benefits, it's going to have AI benefits because you can read directly, right off the tap, you can read the entire data symbol as opposed to needing to do a channel-based model. So I hope that's at least some of what we're thinking architecturally, and I didn't mean to take over the conversation as a commercial, but I wanted to make sure that the question was looked at beyond just spectral efficiency, if it's okay with you, all right? I hope that's helpful to everybody.
All right.
Okay, I'll ask one more.
Okay.
So another thing that's nice about OFDM is the way it marries MIMO with OFDM. Is this also true for these waveforms?
Yeah, absolutely. So the question is, so there's a nice marriage between OFDM and MIMO, and it's absolutely true that there's a nice marriage. Yeah, the same thing is true here. I mean, I think that the thing about OFDM is that you're working in some sense with a projection, and projections change faster than the underlying space. So by working with the underlying space, you get something that's more consistent, and it's not going to exhibit as many wiggles. And actually, one benefit of that, I mean, one of the things I discovered about space-time coding was in space-time coding, if you see paths from two antennas, you get a composite path which is more consistent, slower varying. That's actually really good for applications that live above TCP, because when they encounter packet loss, they ratchet back their rate. If you have a consistent channel, they give you a consistent rate. So that's cool. All right. Well, yes.
What about the latency? If you have, like, EMBB is one part, but then for the going ahead, we see different latency critical solutions. Like in that front, OTFS. So OTFS, where do you see? So when we design a frame structure for OTFS compared to OFDM, can it cater the same latency criteria?
So first of all, I don't think, I mean, OFDM has many strengths, but I don't think latency is one of them. I mean, it's engineered to block error rate of 10 to the minus 1. We could engineer OTFS to block error rate of 10 to the minus 2, and it wouldn't adversely impact it at all. I mean, I think OFDM is engineered to the block error rate at which it sort of works. And it sort of works assuming, what is it called? This kind of incremental redundancy, right? They say every bit gets there in the end. Yeah, it does, but sometimes it takes a while. So you can, so I mean, my meta point is you can engineer OTFS to a better block error rate. And if you're interested in low latency, this might be something you want to do. Okay, I think I was hoping to buy some time. I think I designed a little bit. Okay, do you want? Yeah. Okay, all right, sure, I'm happy to.
How does this work? You had mentioned this for sensing.
How does that? So the question is, can OFDM and OTFS coexist? I don't think it's harder than OFDM coexisting with OFDM, to be quite honest. I mean, in a base station, you will see users use a variety of things, and you know, it's. Yeah, so I think that it's very feasible as an option, and in fact, you really want it to be an option because you don't want a winner-take-all war, I think. Okay, all right, so next one up.
Thank you, Rob. Thanks a lot. I think I even though I've seen the slides, there are some things which I understood it better sitting in the audience. So, and of course, we have to thank him for his unique style of, you know, explaining things with all the pictures and everything. So thank you, Rob, and especially because you took all the pain to travel those 14-15 hours from Duke to India. So thank you so much for that. So I'll request Professor Krishna Narayanan from Texas A&M University to do the honor of giving memento to Professor Rob.
Very nice.
Thank you, Rob. Yeah, sure. Yeah.
We're good.
Full screen करना Okay, so we will have the third session for today. It's titled Industry, R&D and Manufacturing in 6G India. So we have we'll be having 5 speakers today. So let me introduce to you the first speaker, Dr. Aloknath Dey. So Dr. Aloknath Dey is the CEO and founder of TechCrafter.cps. He is ex-CTO of Samsung. Dr. Aloknath Dey is founder and also an industry executive coach through his very popular CTO Crest program. He has been corporate vice president of Samsung Electronics, South Korea, and chief technology officer of Samsung India. He is an adjunct professor in IISc Bangalore. Dr. Dey has 32 years of industry and business experience, including Bell, Nortel, Hughes, ST Ericsson, and Samsung. He has been visiting adjunct professor with IIT Roorkee, IIT Delhi, and IIT Jodhpur. He holds PhD from McGill University, Montreal, Master of Engineering from IISc Bangalore, and BTech and distinguished alumnus of IIT Kharagpur. Dr. Dey is chairman for Ministry of Electronics and IT National Steering Committee for Technology and ICT for Agriculture and Environment. He is a recipient of the Alexander Graham Bell Prize in Canada. He received the IETE Memorial Awards for Distinguished Contribution in Electronics and Communication, IDC Insight Awards for Telecom Innovation, Zenov Awards for Entrepreneurship, and the list, of course, is endless. He is a fellow of IEI and IET. He is also a fellow and governing council member of Indian National Academy of Engineering. So with that, I would like to welcome Sir for entertaining us with his talk. Thank you.
Where do I put this?
Yeah.
Can somebody
हाँ उसी में उल्टा 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 जाएगा हाँ ऐसा लेट मी कम
this?
there's very little space.
Take that.
Put it here.
Just one. Okay, very good afternoon. And, we have grown up reading literature and papers from Professor Calderbank, and it was an honor to listen to him today after so long that we have been working in the field. So thank you for coming and visiting. I'll be talking a little bit about machine communication going towards 6G. That is what we're working. Obviously, when I worked in Ericsson or Samsung, this was more focused on the network part of it, because that's where RAN and the core we developed from 2G to 5G. At least those we have been able to contribute. But now that I'm on my own, and with TechCrafter, which is into cyber physical system, more on consulting, co-creating with fractional CTO services, and executive coach for industry. That's one part, but I'm in the search of a good space in the machine communication to build products and service. So that's the thrust area with which I just wanted to share a few things, how we see it's evolving. So most of the people are veterans, some students. So just one slide to say that, the 3GPP and the release that have been going on. And you see R13 to 16. So that was a space, as you can see, the traffic, vision, and kind of technologies that you first build, then you define in KPI, then the specs get defined, and IMT 2020 advanced that we did. When I joined Samsung, my first assignment was 5G research because 2011, so to 2010, it got started and we built the team, and Anshuman is here, who is from that 5G working to 6Gs. So we grew that way, and 10 years we have been able to see how things work and how we build the tests and trials and then taking to the field. So moving on into B5G, the next 4 releases are 17 to our 2020s, somewhere in between B5G, 6G right time. And then obviously our 21 onwards would be quite focused on the 6G side of it. And as you all know, this is IMT 2030, that is the broad vision. So on the machine side of it, when you look into it, there are a few things. First of all, the number of devices itself are going to be growing. So we used to do what I promised post, the 5G work, that human-to-human communication we have done, and that I think a lot of people will continue. But my focus is now on machine-to-machine and partly human-to-machine. So this is where a variety of devices are also coming. So number of devices and the variety of devices, because you see drones, the HAPS that will be coming, the LEO satellites, obviously, the intelligent mobility that we talk about, the devices and the cars. So this is one set of things, right? And this is where a big change, because you could generate newer sets of devices. And then sensors, very small sensing devices, because low power, can we have them and operate for next 10 years, right? So these are the kind of devices we are talking. What has happened in 5G, the virtualization coming and the slicing happening, private 5G networks is on the rise, right? Even though slow progress of overall 5G, but with that, what we also see that the things that we used to talk under one umbrella are now changing, because then you can say, are these the industrial IoT or is it a health IoT? You will see IOMT, Internet of Medical Things, Internet of Industrial Things, right? So all these classifications, because that private 5G and those specific slicing-based services that are growing. So obviously in that, autonomous vehicle is one thing. I work as in the ministries, one program called Agrionics, where we are combining AI, IoT, robotics to build in the agriculture space how things should be growing. As you see down, obviously you also would see a lot of intelligent elements, whether it is core or your RAN side of the story, the billing, all of those, the AI is going to be in all pervasive, because in 5G it was an afterthought. Whereas in 6G, I think these layers, and as we make more open interfaces, every layer has the opportunity to work in AI inside as well as in the interfaces. So that's one part of it that we can see. The other thing that we see is earlier, your cloud and IP, that was connected to various, whether it is LTE or Wi-Fi or other kind of 3G services, all different rats and networks. Now you're going to be having an aggregator. That intelligence lies in the aggregations, and then we bring in the concept of mobile edge computing as well as the fog computing, depending on closer to core or closer to the base stations, depending on that. So that brings in that intelligence, and it gets bifurcated from there or trifurcated, whether it is UWB, whether it is Wi-Fi, LTE, and others. And we got a chance when in COVID locked-in period, doing research and getting into 6G. So 2020, I spent writing this book along with few others, edited, and this was the first book from Springer on the 6G in 2021 that we published. With that, let me put this slide. And this gives you the crux of the machine type communication. So there are many papers, but in my kind of definition, these are 6 drivers, right? One is autonomous mobility or augmented mobility, whichever level that, level 1 to 5, it can be in any levels. So that's, I think, is self-explanatory. We also talk about connected living, whether it is smart home, smart building, cities, that's what it is. Factories of the future, automated. When you went into Samsung's first time, 2011 itself, I didn't find too many people working and there were machines. But now, obviously, there have been a lot of augmentations, including robotics. That's the future. Data is the new oil. Digital reality, I think from the morning we've been hearing about immersive experiences, going from AR, VR to, if we can get hologram. I'm not sure whether 6G will be able to bring it or it will move to the 7G. But a set of immersive experiences, that is a driver. And the last driver that I see is towards zero world, everything zero, zero energy. It means towards zero, sustainability being a driving factor, and what can you do to do it? Same functions, given 2 solutions, if one can do it with the lesser energy, that will be preferred, okay? Automatically in the standard. So from drivers, we move into the selected use cases. People talk about use cases, but I would think that we should fix first what are the drivers, because that drivers will tell you the use cases with those combinations and not other things that are not primary factors. So one is obviously the connected industry, but swarm networking, smaller, you see entertainment, even Bot Lab Dynamics that's here in IIT Delhi, and we funded them. They've been able to do that nice, firecracker substitute. That's one example, but even on warfare and other things. So swarm networking in one sense. Machines, Internet of Senses, we have not gone beyond audio and video really, except some research literature. But when you bring devices, I can bring INDOs. We might be affected by certain smells and other things. We cannot do that communications. But INDOs could be much faster to detect, right? And a small amount of smell or other things could tell whether a fruit is ripe or not. So Internet of Senses is one thing that we see. Zero energy IoT, which I already mentioned. And alongside that, the personalized body area network is on the medical devices, IoMT, and distributed ledger technology. So I think these are more strong use cases than going into some of these practical things that can be done by 4G or 5G. Then we come down to requirements, and the triangle that you see are the ones that we are already touching: dependability, of reliability, latency, all those factors that are there. Throughput is one, and how do you bring to scalable systems? That triangle is already there, but on top of that, 3 more things that are coming, which is kind of 6G oriented. One is the sensing. Again, we were talking about integrated sensing and communication, so that ISAC technology is one vital, and it plays significant role in machine communication. Efficiency, zero energy, closer to that. We are going to be looking into internet connections, connection density per square kilometer. The human communications, how many people could be there in 1 square kilometer, is one number, but devices could be plenty. Therefore, in 6G, that connection density is a strong factor. And the last part is the security, privacy, with quantum cryptography coming in that post-QKD's time, what will be it? And how do you bring trust into the thing in distributed ledger, traceability included? That is another dimension. So those are the requirements. Now the impact of that in the service class definition, right? Not so clear from far, but just let me highlight. We are broadly looking into 2 different classes of devices. One, critical MTC, CMTC, another MMTC, massive mass MTC. So for example, if you want to do precision agriculture, you can have massive small sensors, long-term energy harvested and put it, but even latency could be there, non-critical in nature. It doesn't matter, little bit errors here and there. It's not going to be different. Then let's say if you want to put an autonomous driving or you want to put a robotic aided surgery, then the latency factor and the criticality factor plays a role. So these triangles that you see is a detailed one whereby if you have a broadband critical MTC, dependable critical MTC versus zero energy critical MTC, how will they change? This is where all the things are, and whatever protocol we define and things like that, we are going to be verifying on these. There would be KPIs listed for these machine communications and saying what's your application and how can you deliver. Now the network will be one which has to deliver all of these, but on the other hand, for specific applications, can we configure, can it automatically detect to do it? I hope you got the hang of it. With that, I'll have 2 more slides just quickly to say the same thing, but different cuts. MTC classifications, you have V2X traffic, IoT nodes, industry, going into your radio resource head units, baseband units, and real-time data analysis. I was talking about mobile edge applications. So how do you do your predictive resource allocations? How do you monitor traffic? How do you thin communications when it's getting congested? There is techniques of communication thinning. How do you do energy efficient onboarding and offloading? Both ways to be able to do. So those are some research problems to say. And this slide talks about specifically mission critical MTCs, because massive communications, you can scale it up because the criticality factor is less. But when you talk about mission critical, this is where many things need to be controlled and to be right. Now, I want to also highlight that there are 2 definitions we are looking. One is a quality of service and a quality of experience. If it's a machine to human communications, I still want human to have a great experience, as if it is talking to another human. So even if machine talks, I shouldn't be frustrated in that communication. So we'll talk about quality of experience in that journey. Whereas if it's a machine to machine, probably experience has less meaning, but all the metrics is it happening. So quality of service, ensuring the time and the commitment and the SLA that we have signed, are we able to fulfill? So you see multi-RAT, multi-network. From the morning we have been hearing different networks, different bands. We'll talk about 5 different bands. Can it be working? Same equipment, but can it cater to multiple bands? So that is what we are looking at, from semi-persistent scheduling to a predictive multi-dimensional resource management. Today, when you talk about spectrum allocations, the 6G would be all about adaptive resource management. Adaptive resource, every resource, virtualize this and that. I can classify, I know what type it is. Can I give the right resource at that point, right? A licensed band, unlicensed band, many of those are working in the present device, your Bluetooth and Wi-Fi. But when you do the band, can we know, what all are coexisting? Can I do a proactive interference management so that the performance is good into that? There would be broker outside operators, that's the proposal again, that will be checking the spectrum and say, if it is not within this, if you're not using, even if you have paid and bought it, but if you're not using, it needs to be released because somebody else is doing. You might get paid, but it will be automatic enforced rather than, oh, it's my property, I hold it. That may be an exception in the 6G. So yes, reconfigurable intelligent surface, new antenna techniques, that's at the physical level, then multi-X, and you do the resource management. Finally, there is a lot of digital twin derivations and software that will be built for smart highways and constructions and real estate in these machine type communications. So to conclude, I just wanted to say that same thing, But yeah, there is a guaranteed latency, and there are concept of how do you tame the tail of the latencies. And last point to say that new service classes, when you do, the traffic pattern would be very changing. See, so far we have lived with Gaussian or uniform distributions quite a lot in various ways. But as soon as we get into this, we will have tons of different distribution pattern. Could be Poisson, could be, we just put a dotted here, unknown distributions, and in fact, through AI techniques, you might be able to even derive what that distribution is, and can you fine-tune that against that distribution of the traffic. So that IAT distribution, and IoT is always event-driven. It's not a synchronous communication. So therefore, how do you adjust to that? So that's the most challenging and expensive part. I hope you got the hang of it. And we use AI in every layer. There are different types of it. I will not go into details, but physical layer, what kind of AI techniques you could apply. You can have principal component analysis on the framing side of it when it's a data link layer, and distributed reinforced learning when you get into the network layer of it. So with that, I thank you for listening rapidly. Thank you. Any questions, comments? Thank you. Yep. Yep.
So MMTC was a major pillar for the 5G, and it was there since the 5G development, 16 onwards. Yeah, but then what is when it comes to an adoption point of view, what is the bottleneck? Like, is it the technology or maybe the other factors?
I think 5G has not been designed for machine to be included in a big number. As I said, whether it is connection density, whether it is type of devices, whether classification of massive versus this. So it's an afterthought. See, as far as we call 5G, but for me, the narrowband IoT, which again came afterthought. It was not designed 4G that way, but people put it later because you wanted to do some communication. So to me, that is the zeroth generation as far as machine is concerned. And 5G is the first generation of machine is concerned. So I am seeing more like a second generation of machine type communications, even though we call 6G, but for machine. Going back to your point, I think it was not, it is there, but it's more human tilted, voice, video tilted, it's not that data centric, so a lot of preemption happens, right? So it gets lower priority in terms of the performance, and therefore it is not. And it also cannot be applied to a variety of applications which is not there. For example, if it's a disaster management, something have to happen, there's a mesh network in 6G, the thought process is, when we need communication most, the tower goes for toss, right? So how do you put a new network, ad hoc network, by bringing drones and other things? So these devices were not there, right? They're not part of the system. So it was never taken into consideration. So I hope that's the key point.
Maybe one follow-up questions. Like, now, having said this, going ahead, do you see that it should be a completely different technology we should adopt for the MMTC?
I guess so. That's why I'm talking. Yes. That's what we are trying to do from my company, TechCrafter, as one topic of the machine communications, only focusing on it and what devices, what classifications, and what contributions has to be made for standards. Yes, absolutely. Thanks. You. Great.
So let us thank Dr. Alok again.
Thank you.
I would like to call Ray to do the honor of. So we need the memento. I think they had a heavy lunch. Yeah. Time for a coffee break, maybe. No, they're coming.
Any other question?
Yeah, please.
Waiting for my last one. You mentioned semi-persistent scheduling. So I agree that has to evolve. The semi-persistent scheduling is great for reducing the control overhead, but in general, it's a bad idea. But what do you think about grant-free access that Professor Calderbank mentioned? And I personally think that when you talk about MTC, integrating grant-free access into the protocol stack is kind of critical.
Yes, I actually agree. Absolutely.
Yeah. So, yeah, sure. Okay, so yeah, so the next talk is by Mr. Jishnu from Tejas Networks. So Jishnu, if you could please come on stage. Jishnu is a principal architect in the CTO's office at Tejas Networks, Bangalore. He has 20 years of experience in the field of telecom. He obtained his BTech in Electronics and Communication from NIT Calicut in 2001 and Masters from ISC Bangalore in 2004. Subsequently, he joined Tejas Networks and is responsible for deciding the long-term roadmap of the company. He has represented Tejas and ITU at ITUT SG15 and has contributed towards the development of ITUT G.8032 and MPLS TP standards. His present interests include 5G Advanced and 6G. He is actively involved in 5G standardization through TSDSI and ITU WP5D and as an individual member at 3GPP RAN. He was closely involved in the design of 3G, 4G optical backhaul architecture with major Indian and international operators. He successfully represented India and TSDSI during the IMT 2020 standardization activity for inclusion of LMLC low mobility large cell as a 5G evaluation configuration in rural e-mobile broadband. He was the founding chairman of Optical Access and Transport Study Group in TSDSI, which developed CPRI front haul standard. Later, he continued as the vice chairman of Study Group Networks SGN and coordinated the effort from TSDSI for including a 5G radio interface technology or 5GI from India in ITU-R IMT 2020. Recently, he as part of the Indian delegation contributed to ITU-R IMT 2030, also known as 6G, framework and vision document, and is presently contributing to ITU minimum technical performance report. He has filed 16 patents, out of which 12 are granted, and was awarded the Best Paper Award by IET in 2006. We will welcome you, sir, and thank you for coming here. Yeah. From this side.
This one, no?
18, 19 minutes.
Yeah.
And we have a couple of minutes of questions. Very good.
Thank you, Sai, for inviting me here. So I would be mostly speaking about what's happening in 5G Advanced and just like extrapolating, at least from my side, on what we would require from 6G. So how can communication sort of expected to improve human productivity? Okay, so few things which we are seeing is one is the evolution of electric vehicle. So this hopefully should by 2030 be a key thing, and hopefully autonomous vehicle should become much more common, and that's the hope for India as to avoid all the traffic jams right now here. Hopefully human don't drive it. So So maybe what Waymo is doing in California, hopefully we should have a lot more here. So that's one thing. So how can communication help in vehicle-to-vehicle communication, whether it's vehicle-to-vehicle or vehicle-to-infrastructure? The second part is all of us, at least in India, the digital delivery is quite common. So all of us, right from morning to evening, get even our milk delivered from Big Basket, BB Daily it's called. We have Big Basket to do some of the other deliveries, Amazon for delivering like a monthly thing or whatever. So there are enough digital means to deliver, but all of these are being delivered by human beings. So can it be delivered by drone? So there are initial efforts in already doing this in India itself. So hopefully we all like masala dosa and we want it crispy delivered at home right on time. So that's the latency requirement we have from a human being. So that's when we say it's done properly. The last, we have one strike going on with farmers right around the corner. They are not allowed to come to Delhi. Otherwise, the traffic jam would have been even bigger. So we want to ensure that they also have a good life, whereby they can sit at home, don't do strike, and basically run the tractors, etc. remotely. So how can communication help enable all this? I am not like assuming like an Elon Musk type scenario that you don't have even human beings to run any of this, but I am just saying from a productivity perspective, how can communication enable all these three? The next part, can communication go beyond networks? So if you see, this is eventually what we would like. So if you have a replica of a city, this was what was done for Boston Harbor. They want to create a complete digital twin of the city, whereby all the objects are sensed, all the communication, if you are connected. So you have two set of category of devices. One are connected devices, which basically have SIM or eSIM or whatever. For that, I need to get a better positioning. And for things which I can't have a positioning thing, I should be able to sense it. The idea is we then create a complete digital replica of cities, which would enable a lot more additional applications to be built on top of it. So what's happening in standards right now? These are a bunch of topics which are being discussed. Artificial intelligence, AI, ML, both at air interface, which is at layer 1, and then at a higher layer, NG-RAN, mostly related to mobility, network energy saving, etc. There is extended reality, XR evolution. So that's basically how do I do edge applications and basically meet the latency thing. NTN, we want to see how the NTN evolves. Specifically, there are multiple different domains coming up. One is satellite. There is also a new category called HAPS, which is also being seriously considered. That looks a much more promising than NTN. Channel modeling is being discussed right now for ISAC, but ISAC is much broader. SON MDT, mobility enhancement. LPWUS is something of interest, low power wake up signal. So you will have two type of receivers, one normal receiver transmitter. The low power wake up signal receiver is like you just, if you want to put somebody into deep sleep and then basically come out of sleep. So this is something which would be of interest on the phone so that you can reduce the power consumption. Network energy saving is specifically of interest for vendors like us. We have been consistently seeing how we can improve the energy saving. Duplex evolution. So ideally we wanted full duplex, but things are quite complicated there. So we are taking step-by-step approach towards full duplex. MIMO evolution. We want to go beyond the 64TR, which is being done. One thing which happened in India is we are mostly deploying 32TR. We are like either 32TR or 8TR. So we are already at the cutting edge in 5G. So if you have to really scale, how do you scale beyond 32TR? 64TR also is being deployed in some portions of the network. And so I'll cover few of them and part of the talk. So if you see today, you have basically TDD, time division duplex, or a frequent FDD. The idea is, can I do a full duplex? So basically, can I both transmit and receive simultaneously? So this is quite challenging because we need to roughly get 145 dB of self-interference cancellation, either at analog, antenna, and digital, or a combination of that. So that is still a lot of work, at least at industry level. So what was initially tried was that if I could actually do what is called within the same slot or a symbol, can I both do downlink and uplink? This at least would allow me to have a lower latency. And because my uplink channels are, if you take the present mechanism, you have 1 uplink and 4 downlink channel. Can I have a longer uplink channel whereby I could basically do a RACH over a longer period of time, so that basically can improve my coverage, at least the initial part. So these are few things which triggered what was called the subband full duplex. So here you can see some of the part is some of the slot thing. On the upper part is uplink and the lower part we can do downlink. So hopefully this would evolve to full duplex with 6G. The second part which I discussed was about a wake-up signal. So this is a serious issue, the amount of power which is being consumed. So this is major, if you want to say in India, this is the most crucial issue, because we already run at an ARPU of $3, which is, I think, maybe in US it's around $45. So that's the level of ARPU at which we are working. The only way is like CapEx is not at all a big cost. So if you have to reduce the OpEx cost. And the key part to that is energy. And we still use a lot of generators to run this. So if you really have to reduce the cost per bit, we have to reduce the cost of energy. So one of this, the evolution, at least in 3GPP, what is happening is, can I make all of this on demand? So the SSB, the synchronization block, can it be on demand? Even the SIP messages, can it be on demand? So that you can more or less shut it down when you do it. And in each layer wise, there can be a separate NES cell which communicates and controls the energy of devices. Only when needed, operate the other bands like 3.5 gigahertz layer or other layer. So that could be a good way. If suppose the handset also implements all this wake up signal and you have a parallel way of managing a separate energy layer and then capacity layer, coverage layer, I can switch on and off depending on the usage. And we are seeing quite a different, so as we deploy in BSNL, we are seeing how each state consumes. So roughly, I don't know why it happens, in India at 3 p.m., there is a peak of data usage. Another peak happens at 9 to 10 p.m. The 3 p.m. and 6 p.m. it actually goes down because I think all of us are driving back home and you can't connect. And at 10 p.m. All our work are over and basically we connect. So that's the 2 peaks which we get. And then, and it's always chatty except at 3 a.m. to 4 a.m. So it looks like India sleeps only at between 3 a.m. to 4 a.m. So these are all some unique thing, and it also changes by state. Okay, so my home state of Kerala does it slightly different. I see a consistent performance from something like right after 9 a.m. to till 10 p.m. It's a consistent usage. So by state, there is a difference, and as we are so culturally diverse, things are all different. So this network energy saving can be done differently by state based on culture and all that. So this is a good area which we see much more work happening in 6G. The key part is we would have to go for higher MIMO. So as was discussed earlier, there is we have reached LDPC coding, polar coding for whatever Chinese reason it came in. So we used to joke to Chinese guys, we are not from polar region, we don't like polar codes during the standard, but it got through. Okay, so right now this is basically, I think we can't do much on coding. So the most likely thing is that we are going to have more and more MIMO. So how do we ensure that the power consumption, it's already 1 kilowatt. I don't think we should blow it up further. So that's something which is of crucial thing if you really have to make 6G viable. On the massive MIMO part, we are, so it's basically, you have seen phase 5 enhancement is about scaling CSI. So we are expected to go above 128 TR at least. So there is discussion already about 4,000 antenna elements and all that. So that's where some of the discussions are happening. So the amount of power consumption, etc., has to be handled. In addition, the CSI information for each of these also is another problem which needs to be handled. So there are other things on multi-TRP. So there is another class of devices called CPs which are coming up, which is multi-TRP. So you can have multiple TRPs connecting to the thing and having higher data rates, at least for fixed wireless access applications. So these are the work happening there. So key challenge here is that how do I still I have to continue to keep my directivity gain similar to what we have today when we go to higher frequency range. So as was mentioned in the morning, the likely frequency range is between 7 to 8 gigahertz, 7125 to, so there is something around 1250 megahertz of bandwidth which is available, and that most likely would be a global band. So the work is around that. So anyhow, you can scale you are roughly going from 3.5 gigahertz, which is getting deployed today, to 7 gigahertz. So you could roughly at least go by a factor of 4 of the number of antenna elements which you can do. So, but then how do I keep the antenna aperture same? We don't want to scale up the, see, the cost is no more electronics. It's actually the mechanical which you put to cool the thermal, the fins, etc. So if you increase your antenna aperture, the cost goes up. Okay, not the electronics is not the key concern, it's the mechanical which is the concern. So we want to ensure those things doesn't change. We remain at those similar antenna aperture and then try to get a similar directivity gain. Coming to AML, which as Rob was mentioning in the morning, basically, yes, too many people are doing AML, so we have to figure out how can you employ them. Okay, so it's now a problem for the industry to figure out how to employ them. So we're just looking at how to understand this much better. So in communication, if you see, you have two parts to it. So there is a deterministic thing which we do. We have segmentation, we have doing some coding, we have do some CRC, multiple levels, one at a code block level and all that stuff. So you have a bunch of functions which we do before we hit the channel estimation problem. So you have an FX which is multi-stage. We have coding. Actual thing we only need to do is coding, but we complicated things by adding some rate matching. You did all of that, and you made it complicated so that we, like vendors, can charge more, but sadly we can't do that as well. So you have multiple bunch of things which has become quite complicated to, even from a deterministic point of view, to understand it. So 3GPP document itself, just to read it it's almost impossible. By the time you implement it, you would have taken few years. And it has become so complicated, it's better maybe, hopefully we are hoping some AML would solve it out, even for us to implement it. So if you see, there is a function f of x which are deterministic. There is an h of x, which is the channel matrix, which we don't know. Through a pilot, we measure it, try to form an h inverse of x in the receiver, and then do whatever we did in f of x, f inverse of x in the receiver. So this is roughly the communication part. So what would happen as soon as we get an AML is that, can I even estimate this f of x? Can f of x be learned using the pilot reports, which was sort of learned over a period of time, so that I don't need to bother about f of x. So for that, light orange box is something like a black box to me. This f of x gets instantiated, and you just have to do the inverse on the receiver end. You may have to inform the other guy. He may also independently learn it, so I don't even have to bother with the receiver. So this is what the effort towards AML is. So we have not reached that stage. So right now we are taking block by block and trying to see whether we can replace it. So one is that, can I do a CSI compression? Because as I mentioned, as we are going for massive MIMO, and we are scaling it up further to what is called an extreme MIMO and all that, should I need to send all the CSI information down to the from the UE to the base station? It's basically, if you see today itself, the DCI is 140 byte, and the UCI, which is the uplink channel, is 1000 byte. It's already quite complicated, and now you are asking it to send more and more information. And the real problem is always on the uplink side. It's never the downlink side. So we really need to sort this out. So we are hoping some AI would come and sort it out. We have tried different models, and at least from Tejas' point of view, we are seeing significant improvement. We are able to compress it quite a bit. So hopefully, but we are not put in real field scenario, but at least initial simulations, we are seeing quite an improvement. Other thing is about beam management. And positioning. Positioning also there is at least industry has shown significant improvement based on AML. The other higher layer, there is mobility, handover, can it be done much more efficiently? So these are all sort of linked function over here. So the end goal is, can I have a multi-stage effects replaced with a machine learned effects? And it's quite important for all of us, because hopefully after that we don't need standards, okay? And maybe I am also jobless after that. So we just want to get out of all these standards. It has become so complicated, even though I am from a standard. So everyone comes and adds more and more things which are like after some time you don't even know why was it added, right? So we need to get out of this. Maybe hopefully AML would do that for all of us. And then as soon as you come to AI, you have to also do what is called a life cycle management and all that. So there is a set of development happening around it. This is quite interesting for all of us, which is what is called the NTN. And here we see at 3 different levels things coming up. One is at a UAV level. So this may not be able to provide communication, but we would have to communicate with a UAV, especially sense a UAV. So one of the issues which we hear from Indian like security agencies, like not in India, everywhere it would be the same issue. You have radars only on the border, but now drones are being built inside the country and basically being used directly from a city. So how do you detect it? So there is no radar right now anywhere inside the country. There may be weather radars, but not the radars which can detect UAV, etc., and appropriate action to be taken. So this is one issue which is a key issue for integrated sensing and communication, and this is also linked to the security part. So that is one use case. The other thing is HAPS. I think in India we have recently had NAL and few other companies running HAPS equipment, which is at 20 to 50 kilometer. They were able to keep it on flight for around 96 hours, so which is roughly a good thing. So we should slightly extend it, because then we could do the Indian test matches, etc. So, but at least it's good for doing an IPL match when we need to increase the throughput quite a bit for a very short time, but after that it's not viable to do that. And the last one is satellites, the LEO GEO, which basically GEO. So what Tejas has been doing is, we have recently worked with, also we acquired a company called Sankhya Labs. So all our fishermen in India now would be having what is called a satellite connectivity to GEO satellite. So as soon as they cross the international border, so it will basically make a sound, so that prevents hopefully people crossing from India to Pakistan on the sea. Okay, so and same with Sri Lanka. So hopefully this would save real human life from being, because right now they are being shot at as soon as they cross the border. So this, we are working with a completely new waveform, nothing to do with 3GPP, and it's much more efficient. So I don't, while Apple is trying to figure out how to send a SOS message, we are actually doing voice call. So they can directly call the Hyderabad sender and inform where they are located. It has a built-in GPS, so the Coast Guard can go and pick the fisherman in distress. So it right now connects to the existing phone over a Bluetooth. So basically it has a Bluetooth connectivity to that sort of a dongle, which then connects to the satellite. The other part is on ISAC. So we are right now working on figuring out the channel model. So there are 2 problems. One is what is called a monostatic, and another is a bistatic sensing. So in the bistatic sensing, the transmission signal is happening from the radio base station, and the device then basically detects there is an object. Hopefully this again would be helpful, especially with Gen Z kids who just doesn't look outside the phone. So if they don't hit somebody, hopefully it pops up an alarm. So the other one is monostatic thing, where the network itself detects it. So monostatic is roughly of interest for Tejas, because of we want to create what is this digital twins of cities and all that, which would be really helpful, where both the transmission and the reception is happening right at the base station. So there are discussions on how do you model each of these, whether it's AGV, UAV and all that. So there is also objects creating hazards, and so these are especially important for railways, where recently there are a lot of issues whereby some objects are put on the railway track and the trains it's causing alarms. So this is something, so this is the key use case, at least from Tejas' point of view, which can make or break 6G, which is integrated sensing and communication. So this could be a place where we don't have any baggage of using OFDM. Okay, so if you really want to introduce a new waveform, it should be in ISAC. There is nothing blocking it. And that's why I was asking Rob that question on whether I should have an OFDM plus OTFS or any other waveform. I would even use an FMCW waveform just to do, because it's basically doing radar, right? It's basically a radar cross-section problem. So I can even do an FMCW waveform. But the key thing is that, yeah, sensing can be completely non-3GPP based just because the other device is not a Qualcomm chipset, okay? Because the object there, you just have to send back, and I am not dependent on it. So the India problem has always been that we never had a device ecosystem, and even for 6G, we don't see that happening, okay? So assuming that that doesn't happen, the only thing where you can introduce a new waveform, etc., is for sensing, and more or less don't touch the OFDM for EMBB and all that, which continues to be the case. And the last but not the least, this is another place where we see a new waveform can come in, is basically batteryless devices or ambient IoT. So this is basically, can you charge, it's like RFID, we quite, in India we use it quite a bit for all our FASTag, all our cars have FASTag thing. The only problem is we get stuck even now because your sensitivity of the capacitor is not good enough, so they still come with a rod. So hopefully with a licensed band, the RFID can be much better. So with a licensed band, I need not have one per track. Maybe I can have a single base station talking to each of the cars separately and then communicate a lot more than just basically the number plate number. So here there are two ways to do it. There is something called topology 1 and topology 2. We are mostly interested in topology 1, which is basically the base station directly talking to the ambient IoT device. Here it's completely new, so the work also has started with completely new frame structure, numerology, everything is being discussed right from scratch. And it can't be complicated because you don't have large energy in that ambient IoT device, so it has to be a completely new thing. So this is roughly what we have, and eventually what we really want is like a society where we can all rest in beaches. EV drives you to a beach. Drone delivers masala dosas and juices are delivered by robot, and hopefully we don't work at all. Okay, thank you. So any questions?
So can you comment a little bit about semantic communication? Is this something that's on your horizon?
Yeah, so this is so this was quite interesting. Okay, so if you see one of those aspects is like, can we just go back to the old voice thing? So there is one devices, I think you may be aware of, Meta and Ray-Ban working on a glass, right? Which has a, I think is a mic and a projector maybe. Same thing Geo is also working on, so they were shown it in IMC, they didn't have a projector. So if AI becomes really powerful, do you really need all this communication of high speed? Can we go back to an old days where we just communicate only through satellite, have only voice communication, everything is told onto your earpiece telling what you have to do, and then I can think even those sort of things are happening. So if that semantic really picks up, I don't need to do any of those. I think the original Shannon paper had told that if not semantic, you have to do all this complicated mathematics, right? Otherwise, so maybe if that really happens and if all the other devices ecosystem really comes in place, maybe you can move out of the handset and then maybe some of this, whatever you're saying. So if the semantic communication really helps in sort of reducing the amount of data which you need to send, maybe we can go back to the whole old voice communication, get things properly working. Space communication especially, it's much efficient to do just voice communication rather than getting into high data rate communication. Latency are within the limit and all that. So that's of interest, but I don't know where it's heading. It all depends on how fast this glasses or goggles comes out in the market, but it's not the Apple goggles. Okay, that you can't use in an outdoor area. It has to be goggles either of Meta Ray-Ban type, or I've seen other companies also working towards it, which is purely, so it's exactly like the Matrix movie. So it should be something of that rather than Apple thing. So yes, it's of interest. Any other question?
So you talked about waveform development in battery-less devices. So since we are talking about these are constrained devices, and waveform development end-to-end is a means computation-intensive process. So how do you do that? The sensors are separate and the computation takes place where?
No. So all of this are happening in base station. Okay, so the device doesn't do anything. So here what happens is you are sending the waveform. You are just getting it initially. So there is a charging period. So during that charging period, it charges. Right now it's a capacitor. So it charges that capacitor, and once it's charged, the second phase of it in the frame structure is just to send out whatever information it has to the base station. All the processing happens in base station. So what you expect from that is some number like asset tracking. So right now in FASTag, you get your car number, whatever your number plate number is what you send. Maybe with if you have a better thing, you can send little more information. But that's it. I don't think you are not expecting any processing to happen at the device level. So all that processing either at a base station or it can be in the cloud as well.
And do you make all that waveform development public or it is proprietary?
No. So this is right now this discussion is happening in 3GPP standard. So if you are interested, you can work there. So right now it's a study item. So that discussion is happening in but it's not right now. Say okay. So let's understand 3GPP where it comes from, right? It's like they will never go out of OFDM or OFDMA ever. Okay. So even I see the discussion initially for low power wake up signal was actually on off keying, which is all you need, right? If you have to wake you up, I just call you your name and that's all you need. And eventually even the OK4 is actually now at OFDM waveform, okay, in a different way, but it's called OK4. So, so I don't know where it heads. It may still be OFDM for all you know, but these are areas which you don't need 3GPP itself. Okay, so we could make a waveform if it works efficiently. Why do you need 3GPP, right? 3GPP is needed when, or any standards is needed if I don't make the end-to-end ecosystem, right? So for example, Tejas makes only base station. We never make handset. But Samsung, for example, does both. Okay, and if their handset were quite successful, they may not even have to bother with all the standards, right? So the standards are needed when you have two different set of industry groups who need to talk to each other, then you need all the protocols, etc. And here in ambient IoT or ISAC, I don't need such a thing. So that's why these are right places where you could actually think for new waveform. But as such, as you mentioned, right now the discussion is happening, but I don't know whether it will be a new waveform. And again, ambient IoT may end. I am hoping there would be another category of batteryless device which may come up in 6G. So that's not ambient IoT. Ambient IoT right now is OFDM. Any more questions? Okay, thank you.
Thank you, Jishnu. So I'll request Dr. Anton Monk from Cohere Technologies to give the memento to Jishnu. Thank you, Jishnu. Can you just put the thing? Prakash. So I would like to invite Dr. Prakash R. So he doesn't need any introduction. I already introduced him in the morning. So he has the unique privilege of talking twice in the workshop today. On this side. So keep it like a little short. like 17, 18 minutes.
Yeah.
Didn't go? Alright.
Yeah. That's the mouse.
not working. I think cursor is there. Which one's it?
I'll open.
Slide 4.
Good afternoon, everyone. My apologies, you have to see me again. But morning we sort of talked about 6G, it's a broad landscape and so on. That talk was supposed to be given by our CEO. And since this is a technical workshop and there are a lot of people talking about 6G, so what I've done here is I've tried to cover. How do I move to the next slide? So we've seen a lot of these, so I'll skip all these slides. The one slide I will use from the morning slide is that we are an OEM. Okay, OEM is we're R&D house. We are also in design house. We work with partners. So we sort of come in this center of excellence funded by government, creating this. So we're part of this ecosystem. So we built a RAN, and I coordinate the RAN. We built a lot of technologies, but since this session is on OEM and manufacturing, so I'll share some of the thoughts and experience we have about the RAN technology development and manufacturing, and it sort of applies to a lot of this ecosystem. And I also we fund other radio developers here in the ecosystem, and we have worked with a lot of startups. And the concerns of theirs and the engagement, a lot of that insights I try to showcase here. So just a couple of minutes. We have built an indigenously developed RAN. It's TEC certified as a neutral body. It's the 5th country in the world to have a RAN. See, Tejas is the other RAN which is mature enough and is going across. So given that this is the 5th country, what is the level of complexity? There are 5 countries who have rockets on the moon. There are 5 countries who have RAN. Okay, sort of. Not this one, but it is a difficult aspect in many things, even getting funding or trying to get into it and trying to qualify it and so on. It is technically complex, logistically complex, and also trying to get it into the stream is also complex. Okay, so we have put our systems in BSNL, in railways. We transferred our technology to some of the manufacturers. Our manufactured systems are on towers for the past 2 years, and started the 5G POCs and so on. And we are also upgrading it to NR, and in the same platform is what is the platform. We are going to use the same one to do our 6G protos and early R&D and so on. Okay, so I'll skip the right side portion. I'll skip, but it's a matter of stuff. So you hear a lot of word about this ecosystem. Okay, so question is what do you mean by ecosystem, right? And we hear the word stack. Okay, we have this India stack and RAN stack and so on. So this is our stack, the C.RAN stack. Okay, so this depicts. This is something that people do. A lot of the Nokia's, Ericsson's, the stack will be vertically integrated. A lot of those are internal, but in this case, C.ROD, we are a OEM. We are the design house, and we work with some partners. So the RAN uses hundreds of types of components, subsystems, modules, and so on. We put them all together. That is where we come in. We are the R&D house and the OEM, and then we transfer that blueprints and stuff to the manufacturers. And these also, Or the RAN manufacturers are small in number. It's an extremely complex manufacturing. First problem we had is trying to convince them it's not just normal digital manufacturing. It's a lot more complexity involved, and because we talked to a lot of these are government funded houses. They were willing to take risk, and they stood the pain. And private manufacturers, lots of them want us to pay them money when we are expecting them to pay us money, okay, as a part of technology transfer. Okay, and then you need system integrators who will take it and go supply this and install and commission and maintain and engage this one, and then you target it into the various segments. So this is like our stack in terms of this. But why did we build it or whatever is we had support of lot of these systems. Tejas were also the other party who was this one. That DOT, TEC, USAFA funding certain portion, the academy have also worked with us, the standards bodies, all these work with us, and we work with tens or hundreds of suppliers here, RF planning, network deployment, the test and equipment vendors, you want to do protos, your mechanical proto suppliers, the element management system, the early this one, and also test labs, third party certification labs. So it's an extremely intricate what you say, or a extremely like a Hydra sort of a technology development program. And given this, some thoughts on this is essentially the manufacturing. As we get into 5G, 6G now, technology, there's a certain amount of technical aspects. Assume that you've solved all the technology, the maths and so on, and then you put in. We've spent about 1,500 man years, more than 7-8 years, but I inherited a team who had already been building a femto class RAM already for 6-7 more years. I'm not even counting that into this, and we're going forward, we will be investing a lot more than this, okay. So and after you have built it, then you have all the other aspects. That is, one is it's a licensed spectrum product, limited market, 3-4 suppliers, and we are competing with big giants who are having billions of dollars of R&D. Then other aspect is we have trouble everywhere, convincing the chipset vendors to supply to us, convincing the labs to work with us, coming at this one, because all of them, the volumes, until the volumes kick in, they were not very keen. Okay, so first is the complexity of the problem, then the volumes are not there, and then the credibility has to be built in. Okay, that is the other aspect. And then when you go there, they expect you to have all the features. Like, when you go there, it's another car. The fact is, you build a car, your friend doesn't care. He'll say, what is the mileage? What is the stuff? So they expect all the features of the 3GPP and so on. And let's say you get past all this, you do all this. But then 3G, 4G, 5G procurement, there's this pulse. And then there's nothing for some time. And procurement, it doesn't happen in it's not like every year they're buying X routers, X switches or whatever. There's this big pulse and there's nothing. Then and the chipset vendors give it to us after they've already dealt with a 2-year window with the other OEMs. And then when you start and when you build, how do you squeeze in and get it into the revenue stream, or how do you build in the revenue stream? That is the other aspect. We were able to sustain, we were able to build. It is because government support, we are funded by the government, and they are like a patient capital investor. Okay, they are patient venture capital. And RF technology itself, the engineers that don't want to work on RF, none of them want to do analog amplifiers and so on, don't excite people. Okay, lots of them want to do machine learning. Some years ago it was Java, some years ago it is Python. Okay, so it is very, very difficult to build a set of expertise. Okay, and it's what we call deep tech. A lot of people think deep tech is only about rockets. The RF development involves a stream of expertise, analog, digital, RF, FPGA, packaging, heat, thermal, protocol, layer 1, layer 2, layer 3, software, hardware, firmware, everything gets into the box. Okay, even though it's just a little box. And when you go and meet somebody, their knowledge of radio planning is low. Okay, we were working with railways and they think it's just like another Ethernet switch or whatever, and I will work with 16 RAN providers and they will all work with each other. That is their expectation. Okay, and trying to convince them, sell them the concept of radio planning, tower planning and so on. And then let's take, you get all past that and then you start manufacturing. Now the manufacturing, India expects a large number of job growth in manufacturing. So there's this big buzz of manufacturing is going to the big thing and it will generate a lot of jobs. The government has a problem of jobs and so on. Manufacturing is 8% of the 6 to 15% of the box cost. So how do you create lot of jobs with only that? And when the whole supply aspect is this one. So one of the thing required is you need a steady and regular flow. That is, every year X boxes get manufactured and there's a supply, consumption is happening, and that is when you can apportion, because the manufacturer also has to invest. You have to publish a line. I don't know that cars come out with new models, not because they put a new model. They run the stream, and if there's still order, they have to make a new line of equipment. So that's why they make a small revision in the respin look and feel and so on. So over the next 5 to 7, 10 years, if they publish like DOD does in the US, saying I will buy so many planes over so many years and this model does this. So sort of a map is put out which helps the OEMs to plan, which is the manufacturing plan, component suppliers to plan. Everybody plans around that. Okay, saying there is some business here, whether it's you, me, 2, 3 people compete. Here we have no idea, no visibility on what is it that has to be built in. And question is now, a lot of times do I get funding for R&D? Okay, let's say 100 crore is the R&D fund given. You build that product, build a technology, build a working product. You still need another 200, 300 crore to do piloting and prove that technology. And to get the ROI on the money, you need another 1,000 to 3,000 crore order, because let's say you do X percentage, you only get so much percentage of the revenue because you're competing in an open market. So if you work on Indian ecosystem development and so on, this is something that we have to look into. So that essentially means strategic partnerships are critical. You need people who work with you, are patient, have invested, and work with longer term aspects. Okay. All critical chips are imported. We are bound by all sort of regulations, Euro export, so you can't even fish around in new markets. You are anyway bound within the same markets and you have to play around this. And taxes is a very important aspect when you work out this stack. And it's not a technology stack. Somebody has to sit and work with the tax Excel and make sure that, where is the arbitrage and what to do and so on. That expertise is also as critical as the, your OEM and APIs and connecting all the RFN signals and so on. And the operators build, they buy $1 billion, $2 billion this year. They sign up for the next 2 years, and that's a small window. They buy very, very small numbers. Where do you squeeze in? How do you get into the supply? And given all this, coming back to where the 6G and the next set of standards. Anyway, I was talking about 4G, 5G and around that, but this problem is going to repeat. This is not only for this generation. This is something I've been seeing from 2G, 3G, 4G, all over, 5G. So 3GPP, one is it's become a behemoth. It's become like really huge. Okay. So the operator also expects your box. Right now, whatever we are putting into the box is having 4G, narrowband IoT and 5G. They were also asking for 2G and if possible 3G. We refused 3G. 2G we said we'll look into it. You give me an order, then we'll look into it. They're expecting upcoming future release 16, 18, 19, 20 and so on. So essentially you will have to put in all of them and the stuff is there. So question is, how many people in the world can put all the 3GPP releases into a box other than the already established 3-4 players? So what has happened is it's become this IBM mainframe like which only IBM can make. So maybe it's ripe for disruption. It is something that it is probably going to collapse on its own weight, because other than those, and even those companies cannot keep, it's getting bigger and bigger with the customer value is small. That I think you do interworking, you have to push a product into the RAN, you have to test all the features and get this one. So and what is the value to the customer? We are talking to an operator and they told it provides 400 features, we use about 130. The remaining we don't care. In fact, we asked them to disable because you enable it, we have to train all our staff. Okay. And this is where I look at, it's like Windows maintenance. You keep maintaining lots and lots and lots of drivers. What is the use for you? So maybe if you're putting up a data center and you want some sort of operating system, a small Linux kernel is what it requires. You don't need all the versions of Windows with all its history and baggage. Okay. Open RAN was supposed to solve a set of things, but people underestimated. If you take working modules, put them together, how long does it take to prove a product? It's like you want a car. I'll give you all the modules. You can buy something from Bosch, you can buy Fiat engine, something like that. How much time does it take to put all these modules and work a car and prove it? That is 85% of the effort, the proving. making a product. The modules is the smaller portion, which is something people, from the time your first call is done, where all the modules are in place, to the time the product comes out, you have 85% of effort that is still pending, okay, which people do not, understand. Now, question is, we don't tell too much to discourage, we don't want to discourage people, we don't want to tell youngsters who are working that still a lot of effort is there. If a new joinee comes and you tell, now you have done a call and so on, okay. None of the newer bands, as we go, they are not addressing coverage. The question is, I'm not sure how our life is going to improve in doing all this effort. You put millimeter wave, all the effort that went in just got burned down. The operators returned the spectrum and it just, threw all the equipment out and whatever. It's just consuming power with no value, right? And next gen, as we go in fact, rather than making it simple, they ran their virtualization getting added, this one is getting added, more security problems, more hazards, and complex interface. Even though you put virtualization, you will have to still get an accelerated. Telecom has always been an accelerated computing segment, so product. From the time I joined, there were always accelerators inside the processor. Okay, and nowadays you're on top of it. You're having NVIDIA, who made a graphics processing unit, and trying to tell the graphic processor unit is the RAM. Okay. Rather than saying what do you need, the way I look at it is what is a series of minimum number of atoms that you need to put in to see this calculation being done. That more is a SOC problem rather than a GPU problem or a Xeon problem and so on, right? And overall, as we look into, let's say I want ubiquitous coverage and I walk around and every lamppost is going to have radio and this one has a radio, I have a radio. Maybe the way we all look at RAN and the radio and needs a relook. We sort of try to, cut down the complexity where there's radio reception, transmission, and then you have APIs which manage the end-to-end using other automation and so on, rather than the existing large behemoth with which nobody else can interface other than their own equipment. Okay, so these are some of just my observations based on past few years of R&D. In fact, we have burnt our hands in many technologies. This is many generations of stuff. So this generation, we managed to push it out from the past few years. And now this is something that is going to happen when you become an OEM and when you start getting into manufacturing. It is a lot of this problem still existing. Maybe only the RF will get removed, but all these aspects has to be addressed. And if Indian ecosystem and Indian development has to come in, okay, we all have to sit and solve this problem solving. It's a mega problem solving exercise with a lot of heads of a lot of areas of expertise sitting together. Okay, so that is just a small brief. I try to not talk about the standard 6G, immersive, XR, artificial intelligence and so on, because I knew there's a lot of other people who will put up those slides. So just some insights from what I have. I hope there's something useful. Thank you. Any questions? No? No interest in manufacturing?
I think you made a lot of interesting points. So for a country like India, I think a certain baseline coverage to everybody, for example, let it be 1 or 2 megabits per second uplink and downlink across the country. That's really, I would say, the primary use case. And all these low latency or ultra massive stuff can come later in other maybe special circumstances or deployed locally in specific areas. It need not really be something that pervades across the country. So with this in mind, I also agree, I'm just adding to your talk, that I also agree that it doesn't hurt to relook at technologies and say, what is the most minimalistic technology that can provide this quality of service ubiquitously across the country?
Yeah, thanks. That's, in fact, morning I was telling, maybe satellite, if I get coverage all over, even I'm willing to do with a few tens of kbps. I'm just willing to say where I am and ask for help. I'm still happy with that as we go further and further away. And 1 and 2 Mbps, I think, is as good as what I am getting now in some of my office. I think my office in Electronic City, and I have 2 operators. One operators I have 0 coverage. Okay, so, and all the time I go talk about satellite, rural communication, drone, apps, everything. I give presentations, and one phone doesn't work in my office. I'm in Electronic City. I don't want to name the operator. I mean, I don't know the logistic issue, but that is how it is.
Thanks. The truth is, I mean, if you want ubiquitous coverage, GEO satellites support NB-NTN right now. There was a demonstration in India just a few weeks ago with Viasat. It's a product that I used to work on when I was there direct to sell. So the question is, what's the definition of ubiquitous coverage? So if all you want is emergency coverage, the capabilities are there. If you want a megabit per second, maybe, but what's the population density? So so I mean, it exists in 5G right now. I think 6G will bring better service continuity, but there are solutions that support that now. Just a comment.
Yeah, I quite agree. I mean, even though it is there, we are also all watching, the Starlink versus this versus the local OEMs. They're all battling it out. It's regulatory come. We are not sure what is the parameters of evaluation. That is beyond this one. But the ubiquitous coverage, when we were doing standardization, part of me, Jishnu, and some of us, we were battling it out in the ITU and all the places. People in Australia, Germany, US, all of them told that they also have the same problem. Rural, outside the coverage is zero. And which was like I always thought developed countries have it, only in India we have the problem. But looks like Germany has large underpopulated areas, which is not worth investing. Then all of the operators are private, nobody invests. And US, my friend says, I'll lean out of the window and call. He calls me, okay. And I'm sort of better. I'm sitting on my sofa at least, So, I mean, it looks like it's a universal problem. So that's why I say some amount all over if I can get in. Okay, fine. And anything else? Thank you.
Thank you, Prakash.
Thank you.
So we'll take a small tea and snack break. It's just outside the auditorium. And then we assemble back at 5 p.m. So we still have 2 more talks in this session, and then we have a talk by the Secretary DST, who is in the Prime Minister's office right now. So it'll take him about, an hour to come here. So he'll be here around 5:45. Hopefully by that time we'll be able to finish the other 2 remaining talks in this session. Thank you. Okay. So, so can we request the delegates to, because we are going to start the remaining part of the session now. So Rahul, can we request delegates outside to come in? Okay, so we'll start the remaining part of the session. So we have two more talks in this session. So the first one is by Mr. Abhijit Masal. So Abhijit, you are here? Yeah, please come on stage. So Mr. Abhijit Abhimanyu Masal serves as a lead research engineer at the Center of Excellence in Wireless Technology, CVIT, which is based in Chennai, India, where he has amassed over 10 years of extensive experience in wireless standardization, leading a dedicated team at CVIT. He oversees diverse projects encompassing cellular technologies such as non-terrestrial networks, positioning and sensing technologies, and vehicle-to-everything communications. Since 2017, he has actively contributed to various standardization bodies, including TSDSI, 3GPP, and ITU. He is currently vice chair of the study group on networks in TSDSI. In 3GPP, he represents CVIT across RAN 1, RAN 2, and SA2 groups, participating in plenaries since release 13. Currently, Mr. Abhijit is involved in advancing 6G technologies activities in CVIT. So we'll be talking about what CVIT is planning for 6G, right? Thank you. Thank you, please.
Okay. Okay. Good morning. Good evening, everyone. I think. So I'll just briefly give the aspects that I am looking in a CVIT, and which will just give a guideline on my presentation. So presently, I'm working on the 6G standardization effort. So just to give a bit overview about the CVIT, CVIT works on the standardization effort, mainly on the cellular domain. So we've been there since WiMAX time. So we were part of WiMAX. Later on, it was in 4G, 3GPP, 4G flavor, and then we were actively involved in a 5G since release 15 onwards. So we've been working on a lot of aspects in 3GPP. So including MIMO, then reference signal design, the waveform designs, and so on. So now my focus here for this present talk will be on our view on 6G standardization point of view. So I will again, we also part of IMT 2020 activities in in ITU, WP5D mainly, the group. So because that is the forum where the requirement will be set, and the SDOs, the standard defining organizations like 3GPP, will start delivering on the requirements that have been set by the set towards the next technology. I think everybody knows about this here. So I will not go in detail about this, because this hexagon is pretty sure everybody know about right now. But then the main focus, or maybe the new things that have been brought is about this hexagon, is the three new verticals, which is sensing, AI, and ubiquitous connectivity. So from India point of view, ubiquitous connectivity is something that we see it is important, and I'll talk about this in detail. What are our plans towards it? Going ahead, this is because, as I said, I will be focusing more on the standardization forum related aspects, and mainly on the 3GPP front, because that is where I represent. So this is the timeline that I think we will be following in 3GPP towards the standardization activities. So as you know, there was a very high-level workshop on use cases which happened this year in a May. Where the use cases are being defined, and the use case, the stage 1 specification are actually started drafting towards it from the use cases point of view. And if you see the use cases, I think most of those use cases have been talked about, or at least the guideline has been talked about is in the morning session. How can we increase the market adaptation of the features that we are bringing in, and how can we optimize the capex and opex solution, opex of a whole deployment as such. So on that front, the discussions are happening in a 3GPP SA1 group, which is a stage 1 standardization group. based on that, we are expecting a workshop in a March, which is three months down the line, where the things will kickstart in 3GPP for taking up the 6G related study, which will last for 2 years, as you can see from the time. And then it will go ahead and we will do a normative phase, which will be a release 21, which we'll call as a first 6G release. Right. Now this is overall a plan for workshop agenda. I just put it for the information, which will be in the March, where the different presentations across the stakeholders will be discussed. In 3GPP between the architecture group as well as the RAN group. And the next discussion will happen in the June, where the things will be finalized towards the objective for the studies. Now, as some of you might be aware about, is that whenever there is a new technology will start flowing or start getting developed, there will be two streams, because there will be a legacy technology which needs to be evolved, and the new technology or a new technology has to be start from somewhere. So that is what even in this case will happen. So as we know, 5G Advanced is something that we are right now doing, and then the 6G will come in. So 6G will branch out from that. So now the discussion among that is also important, because how much we should do in the next release of 5G and how much should we do in the 6G, and that completely depend upon how the operators and how the market and how new services are actually coming up, whether they are very important and they cannot wait for a next 3 or 4 years development for the 6G, and we need to do it in the 5G, or we should wait for those services. Accordingly, the 3GPP will decide the split, which will happen in the month of March, the next plenary meeting. So we have a two main overview for that. Like we can have a 50-50 split, like 50% of the work will be from the 5G Advanced as a evolution of whatever 5G we are taking up, or we can just reduce the work for the 5G Advanced and we'll completely focus on 6G. So I'm just putting the discussions and the talks that we are having with the different companies across the world, and putting forth the ideas that company has, so that everybody will understand how things are being discussed and debated around. So this is the thing. To be very frank, from our point of view, 30-70 is something that is the good split, where we can do a 30% of work on 5G Advanced, where we can just focus on how can we improve the 5G services itself, and then rethink about the 6G fresh from the new or a disruptive technology point of view. Now, around the verticals, if you see what are the technology will be the drivers for the 6 verticals I just mentioned. If you just consider the immersive communication, because immersive communication is equivalent to EMBB communication, roughly speaking. So that will be driven by your extreme MIMO, distributed RAN, then mobility enhancements, then energy efficiency, new solution for FWA and RIS kind of applications, then the integration of AI ML in a RAN. Then coming to the sensing, which will be then coming to the hyper reliable low latency communication, which is an extension of URLLC, which is expected to improve in this particular release. Then ubiquitous connectivity. For ubiquitous connectivity, a lot of topics have been discussed. One of the important topics is integration of satellite with a terrestrial network. So and then another HAPS communication, or even we can think about a large cell deployment and how can efficiently we do that part. So that is another aspects that are being discussed under the ubiquitous connectivity. Then coming to the massive communication, I think some of the speaker in the previous discussion, it's talked about that massive MIMO, so MMTC was not actually was an integrated part of the 5G, but it was been brought in later in some form, but which was not been evolved fully, but it is expected to evolve in a 6G. Then very important and promising vertical is integrated sensing and communication. So for the integrated sensing communication, the positioning is also one of the aspects which will be part of things. So under the integrated sensing and communication, there will be three kind of divisions we can see, where we have a positioning services where a device will be a cooperative device where we like a UV, and then there will be non-cooperative devices where they are not having any kind of connectivity to the network. So such classifications can happen here. Now I'll dwell into a little bit of our understanding or what are the topics that are important from our point of view. I'll talk about the immersive communication first. So for the immersive communication, there have been some discussion on enhancing the beam management. So beam management enhancement, I think it will come from the new spectrum that have been investigated for 6G. Mainly, I think I think it has been talked like 64T, 64R are the promising areas, new promising areas we can look for the 6G point of view. Even we are saying we can think about 128 ports as well, especially for FWA kind of applications and maybe very fixed wireless services and CP kind of devices we can do. With FR2 kind of spectrum, which is 7 to 24 gigahertz spectrum, which is talked about for the 6G applications. Similarly, we can do some kind of CSI enhancements for better spectral efficiency and reducing the overload of the CSI feedback mechanism. Which can include AI ML aspects to be considered. Similarly, we can think about some kind of non-DFT based precoding, like non-linear precoding, can be thought about to cater a better gain. Now, second part is a distributed RAN. I think in the literature it is also been called or termed as a cell-free MIMO. Which also can be one of the factors which is important for the from the MIMO or from the EMBB kind of applications for the immersive communication kind of applications. So that can be done by multiple factors. One is handling the handovers phenomena. So wherever we have we can have some optimization with the handover, and seamless handover aspects can be brought in by using an AI/ML. The second part is the dual connectivity and carrier aggregation enhancements, which is integrated part of a 5G system, 5G and 5G advanced system, but that can be improved further to have a different kind of carrier aggregations across different bands. So it will be termed as non-synchronous carriers. So non-synchronous carriers, something like you have FR1 and FR2 aggregations smoothly, or even NTN and TN aggregations, which can be done, which is not a part of 5G right now. So 5G won't support a carrier aggregation for the NTN services, which in a sense is a bottleneck for a capacity in our NTN systems, which can be removed going ahead in a 6G systems. Similarly, I think FWA and CP devices are anyway gaining popularity in the deployment. So which we see that there will be another area which can be improved further, mainly from defining a very lighter stack which is very catered for a FWA kind of application, removing a lot of other features which are not necessary. Similarly, the lean protocol stack. So for example, when we have right now, I think if you see the stacks, L2 and L3 stacks are generalized across all the traffics. What has been found by our analysis is that for at least for some of the applications, for example XR and VR kind of application, it is not necessary to have all the stacks or the processing at the every level in the L2, which can be optimized, and that will be another possibility companies are talking about, and we are also actually seeing a gain in that. Then coming to, I think there is a repeater kind of application where to extend the coverage in a given area. 5G Advanced has specified the NCR, which is network control repeaters, which is a very lightweight repeater strategy, which I think can be evolved to support RIS kind of applications for a coverage enhancement. And that is also one of the important factor for the ubiquitous connectivity approach that we are thinking about. Now the next topic is the energy efficiency, which will drive the 6G more or less in a big manner. So because if you talk to every company, every vendor, they will talk about the network optimization. And then energy efficiency and overhead saving is very important factor on that. Some of the aspects we are actually studying right now in 5G Advanced. And now but then the aspects that we are actually looking in a 5G Advanced are the bottleneck are the initial 5G design itself. So when we start thinking about a study in a release 20, eventually when we go for a normative phase in release 21, the energy related aspect will be one of the KPI that will be on the day one. So when we talk about the new RAN architecture. So that's the overall sentiments across the industries, and that is we see it is one of the important factor for 6G. So having said this, the solutions will be like we have to look upon the RS design aspects, any efficiency that we have to bring from energy harvesting, then network configurations, how do we optimize that? Can we use an AI/ML to do these optimizations? So these are the aspects will come in. Another aspect is I think it has been talked by one of the presentations in the morning, I think Jishnu, like duplexing. So we will be working since 5G. I think we tried to bring the 5G full duplex system in the 5G. 5G at least not explicitly but implicitly it supports full duplex, but it has some bottleneck. Because we will not be able to configure because of certain aspects. So that can be diluted by using a duplexing enhancements, especially full duplex that we are eventually seeing. But right now the sub-band full duplex approach is being standardized, which we see has a potential to carry it over in a 6G also. Now coming to AI/ML, I think this slide explains more. MIMO is very important for the AI/ML optimization point of view for the file layers, and basically from the mobility point of view, mobility and beam management. CSI is another aspects, but the beam management and the mobility are very important from the AI/ML point of view. Now the next KPI that eventually IMT 2030 will finalize is a localization, so positioning. So positioning will become as an inherent KPI for any deployment. So in that case, positioning related services or even a positioning as a feature in the RAN also is one of the important factor, because by using the positioning we can optimize lot of factors in the RAN. For example, the scheduling, your CSI acquisition, even AI/ML model training. Positioning can be one of the inputs which will optimize overall performance of position or AI/ML model. And the next little bit far-fetched or maybe a bit extrapolation, or I would say it's like in a nascent stage right now the studies are, but a promising one is like neural phi, where every block of the physical layer we can replace with an AI/ML model, right? So that is another aspects can be thought about. But to be very frank, in 6G this will not be the day one approach. Eventually it will come, but there are some literatures people are thinking about. But from the industry point of view, or at least 3GPP point of view, this is not so been talked about. Now coming to ubiquitous connectivity, our focus is on the NTN. So I personally involve NTN from release 16 onwards. So we have been doing release 16 study, and eventually in release 17 we were involved, where this TA-based solutions were been proposed. I was part of that. So that we see a very potential, has a potential impact on ubiquitous connectivity as such from the Indian context point of view. So we see like they should have a seamless integration from NT and NTN from the day one when it comes to a standardization. So which will help even network, terrestrial operators to work with the NTN operators, or maybe a terrestrial operator can become an NTN operator and give an ubiquitous connectivity or a services in an uncovered areas. As I mentioned, positioning is another aspects which will be talked, which is being a part of 4G and 5G, but 6G it will come as a network function. So as a network feature, in a RAN feature. So that will be another direction, or it will go. I think integrated sensing, as I think it has been discussed by many speakers here, but that also we are thinking it will be, because this has been talked about by everybody, almost everybody. So it is for sure 6G will have some of the solution as a day one on this. I think another part is an IoT. So ambient IoT is IoT like a RFID kind of IoT connected to the cellular. This is something is very much important, at least has a potential for a massive IoT kind of deployment where batteryless solutions can be talked about. So right now it is being done, study is being done, and I think this is one topic that will be taken in the 5G Advanced. But it can be evolved in the 6G as well. So this part of our discussion was on the RAN, but then we also work on the core network architectures. So from the core network point of view, we have categorized our whole solution on 3 fronts, which can have a potential impact in 6G. So one thing is very sure that 5G core has gone a massive change in a 5G compared to 4G. And we do not expect any new things, at least a disruptive changes in a core networks in 6G. But what might happen is an optimization in some front, because if you see the specification right now, it is very bulky and sometimes it is very redundant in some places. So that optimization can happen mainly from the energy efficiency point of view, user exposure point of view. So user exposure and an exposure function enhancement is very important aspects. And the new services like NTN will be brought in for the core network point of view. So I think that's it from my point, and then I think AI/ML definitely will be another aspects we will work on core network, because AI/ML has a very good potential to be adopted in the core network, and that is another aspects that 6G will have a potential to. Then that's it. I think that's it from my end. Thank you very much. I'll open for questions. Okay, yeah. So our main focus will be on ISAC and NTN. These are the 2 main focuses. And definitely a MIMO, because MIMO we've been doing it for 4G, 5G, and we will see definitely what are the new things that we can do from the MIMO. But then at least my personal opinion, MIMO, a physical layer, has done what it can do so far. And in 5G itself, it's mature enough. The drawback for the 5G is, I think, higher layers, L2 and L3 layers, which needs to be optimized in some sense to adopt MIMO very effectively. So that I think we are working on. Apart from that, as you coming to your question, our focus area will be on the ISAC and NTN. Yeah. Sure.
So as an operator, what will be his primary objective? Like it's a business performance or platform performance? And how it's going to complement each other?
Yeah, so it depends on the stake of a operator in a both of the areas, right? Like let's say service. Exactly. I think going ahead, the platform also becoming a very integrated part of an operator's infrastructure itself. So I would say both, because right now, ultimately, maybe like a cloud services itself, right? Like right now there are some companies which provides a cloud services, but why not operator itself can provide the services by themselves? Yeah, but then so what happens?
They're already providing 5G, many are providing, and 6G it's going to be
Yes.
close, but they're much more enhanced apart from that as well.
Exactly. I think the core network for this kind of services was the support for that has been brought in the 5G. We will see that it itself will get evolved. So on that front, nothing will change. But what might happen from the operator point of view is, I think what is being done from the RAN side is energy efficiency. How can I optimize my energy consumption so that I can reduce my OpEx? So that is the target from the operators.
So what's the percentage performance optimization it is getting?
Oh, I don't.
4G to 6G?
I don't have numbers. I don't have numbers as such on that. But then, I think it was been talked about also. It's like lot of right now also to run the RAN, the continuous RAN, it consumes lot of OpEx. Okay, and then many times the traffic patterns are different across different regions. So why can't we actually adopt to these patterns, and we can switch up some of the infrastructure when it is not being used. So right now, this has been done as a 5G advance, but it has its own difficulties because the initial design of 5G itself. So 5G design itself won't allow me to shut down some of the RAN operations, though it is meant that it is on-demand services. So though the design was on-demand, but some of the services are not been designed as an on-demand. For example, initial access. So that is the bottleneck, and I think from the energy point of view, it will be designed. How can I make it energy optimized? Yeah, thanks.
Yeah, I was going to ask you a quick question. You've partially answered it. Do you have a specific target in mind for energy per anything, or is it just make things better?
Yeah. So, okay, when we say from the RAN energy, the energy per bit is a good criteria, but then is it really can be achieved? So that's a main part. I don't have a direct answer to it because we're analyzing this part right now. Like, can we really go ahead and define a KPI as an energy per bit and work around the solution around that? Because it's a bit difficult to digest the fact that I can do my design very cater to that particular KPI. It was been thought about in 5G, but never been accepted by a community. So that's
Okay,
it.
so very quickly, I just want to explain why I think that's really short-sighted, and that is, some time ago when we were in a 2G world, a lot of people said, this is going to be the design, let's see if we can reduce system noise. Qualcomm looked at soft handoff, which turned on 2 transmitters at the same time. Everyone said, you're crazy, we're trying to limit system noise. It ended up lowering system noise because in the soft handoff region, power was reduced on both sides. So my point is, once you lock in and say, we've already got the right physical layer, we're still going to stay in a codebook world, but we're going to use AI, and then we're going to do some kind of sensing network, and then we're going to do the best we can on power, it's really not going to end up in the right answer. If we put a stake in the ground and say, where are we using power and what alternative designs are available to us to reduce power, it will open our minds. That's my suggestion, okay?
Thanks.
Let's thank Abhijit. So I'll request Dr. Sandeep Sharma from Tech Mahindra to give the memento to Abhijit. Thank you, Abhijit. Thank you so much. Thank you so much. So our last talk in this session is by Mahesh Basavaraju from Road Schwaz. So Mahesh, if you could come on stage. Mahesh Basavaraju is a market segment manager responsible for driving market position for the wireless communication segment at Road and Schwaz. He is a delegate representing Road and Schwaz in standardization bodies like ORAN, as well as responsible for developing and implementing market and product strategy. He focuses on both cellular and non-cellular technologies and is active in conferences and workshops in the Asia region. Mahesh has over 19 years of experience in test and measurement and has previously served as an R&D engineer at Nokia. His experience in working on both mobile device and network equipment testing has contributed to his comprehensive understanding of the wireless industry. Thank you, Mahesh. So over to you now. Yeah. So you have your, yeah. So you can keep it to like 17, 18 minutes.
Thank you, sir. Thank you. Good evening, ladies and gentlemen. Welcome to the workshop and to the last topic of the day. And I believe this presentation would be a perfect climax for this technology sessions today, because almost all the speakers have resonated well on what are the research candidates for 6G, and I'm going to shed some light on how these candidates can be tested. And some of the speakers have also highlighted the importance of test and measurement when it comes to the new technologies. Yeah. So without further ado, let me start with, yeah. So this is something I think everybody has focused on. What are the differences between the past generations and the new generation? And for me, I believe any new technology would be success provided the new technology would make way for new devices of different form factors, and also it caters to the different applications and use cases. So that is the differentiator, or that is the key ingredient which makes a technology a successful technology. And do we have the key ingredients in 6G? That is what we are going to see. And also, as we have seen from already the 5G Advanced, we see the technology is being adopted by the various verticals, like say in the India Mobile Congress, for example, all the network operators and chipset companies, they had a car in their booths emphasizing that the automotive industry is embracing the new wireless technologies, and likewise. So you have seen the different use cases, which were in case of 5G, the eMBP, massive machine type communications, and URLLC. And now with 6G, we have a broader perspective, and here we have newly the immersive communication, and also new cornerstones, technology cornerstones being introduced as part of 6G, namely the integrated sensing and communication, ISAC, and then also the AI and machine learning becoming a native part of the 6G network architecture, and also positioning and hyper reliance, low latency communication becoming important. So this, on the left-hand side, you also already see what was addressed as part of 5G Advanced, and with IMT 2030, what would be the new capabilities we are looking at, and most of the speakers have already emphasized on this, like say integrated sensing capabilities would be one, and then AI, sustainability, would gain importance, like say the network energy efficiency or network energy savings, and also positioning, coverage, ubiquitous connectivity with the advent of NTN, and so on. And so it's no different, even from the Rode and Schwarz perspective, we have these research candidates for 6G, starting from new frequency spectrums to be explored, like say terahertz communications, sub-terahertz communications, and also the FR3 or FR2-0, which is the frequency between the 7.125 gigahertz to way up to 24 gigahertz. So that is the spectrum which is kind of interesting and gaining momentum within the industry to be explored for communication. Yeah. And secondly, we have the integrated sensing and communication. So let's also explore what are the test requirements, what is the testing aspects when it comes to exploring the integrated sensing and communication related research activities. AI, RIS, reconfigurable intelligent surfaces, photonics, and then we have new waveforms about which Mr. Rob already highlighted in a dedicated session today. Ultramassive MIMO, so that is a massive MIMO beyond 128 TR or maybe 256, 1024, and so on. New network topologies. I'm also a delegate representing Roden Schwarz in Open RAN Alliance, and here we also see this in 6G. ORAN would be a native part of the network topologies, distributed computing, and full duplex communication, security, and trustworthiness. So given the time, I would show some of the dive into the test and measurement aspects for some of the features highlighted here, but not on every aspect in this session. But of course, you are free to approach me if you want to know more about any of those candidates which I have left apart in this presentation. Now coming to immersive communication. So here immersive communication requires more data rate, more throughput, and in that we also have, from a testing perspective, new KPIs. Like say, for example, it's no longer round trip time, which is counted for latency, but also the motion to photon latency, which becomes important to have a better quality of experience for those XR devices, extended reality devices. So there we have, say, for example, the metaverse. So wherein we have, this was an interesting demonstration always from the last two Mobile World Congress in Barcelona, where we had these XR devices which are kept inside, say, for example, a chamber, and here we have, say, for example, a phantom to which the gear has been mounted, and then we have the base station emulator, which emulates a network in a test bench where you have control over all the parameters. So this is a base station emulator which can communicate to the external internet or cloud services where your XR content can be hosted, and then we do an end-to-end application testing, and also simultaneously can move the phantom inside the chamber in different directions, different angles, to see how the RF and also the network impairments, like say some delays, jitters, could impact the quality of experience. So this is a demonstration we have been putting up from the last 2 years and has been gaining a lot of attention in the industry, and most of the companies are also focusing on XR because that is where we think the network operators can also generate revenue because they are data intensive devices. Yeah. And then we have, say, for example, to support such metaverse applications, we need very high data throughput, which means we have to explore the higher end of the spectrum. Like say, so far in 5G, it was millimeter wave. With 6G, it could be sub-terahertz, that is the 110 gigahertz, 170 gigahertz, and also the 330 gigahertz. We know countries being working on these frequencies, exploring the channel models, doing channel sounding measurements to see how the propagation characteristics would be at these very high frequencies. So for that, Roden Schwarz, we are prepared with our existing vector signal generator analyzer combo, and we have also built new products like the frequency front ends, and also frequency converters, which can enable our existing platforms to go up to those very high frequencies. So these are some demo setups which you can see. So here we have especially this generator called SFI, which can support up to 10 gigahertz modulation bandwidth. And likewise, we have front ends going up to 110, 170 gigahertz, and also 330 gigahertz. And yeah. So these are some of the impressions which I can provide you. If you need more information, do feel free to approach me. And then on the other hand, we do have need for new waveforms. So that is very well covered in the dedicated session by Mr. Rob, and I leave it there. So from generation to generation, we have seen the waveforms shaping right from TDMA, CDMA, OFDM, OFDMA. Now, what would be the next waveform candidate? So here again, we collaborate with Cohere Technologies, and we have these same platforms, the generators and analyzers, wherein we could generate the OTFS waveforms and analyze these waveforms. Yeah, this is also a kind of like as mentioned in the slides, it's one of the attention grabbers in the Mobile World Congress year on year, and yeah. So while new waveforms, so also another motivation for new waveforms could be like, say, we are now no longer looking at a communication world wherein it's all about human talking to human, point-to-point communication. But whereas we are moving to a stage where communication plays a role where we get the data from the physical world through sensors or other means, and then there is a digital world where we act upon those data collected from the real world, physical world, and then use techniques like machine learning, artificial intelligence to enhance the processes, optimize the process, and then, yeah, in a way to enhance the quality of experience for the end users. Yeah, so this is what we are moving towards. And in that perspective, we have the integrated sensing and communication, a lot of use cases where you can see catering to the different verticals like, say, medical, smart cities, smart manufacturing, and so on. And these are the different use cases. Is it new for us? Maybe we had it as discrete elements, like, say, we always had the communication channels. We know that 2G, 3G, 4G. And then we also had the radars, the sensors, sensing technology, both acting or as independent technologies. Now they are being integrated onto a common platform, and that is new. So what would we need from a test and measurement perspective to recreate or to do research and development activities on ISAC would be something like, say, for example, on the communication channel, the KPIs have always been throughput, block error rate, measurement, and if the end device supports video, audio, the quality measurements for video, audio like Polka and so on. And then for the sensor channel, there the KPIs are different, like, say, detection, the accuracy at which I can detect those objects, and also the resolution if there are two objects very close to each other. So those are the KPIs, different KPIs coming from the two different worlds. And now this has to be, when integrated, common test platform should be able to cater to these, or should be able to support your research activities while realizing these KPIs. So in that perspective, we have, say, for example, the communication channel, we have always the generators and analyzers, and also we have these instruments for generating interference. And then here we have this new box, which is also catering to the automotive sector, like, say, in generating the echo generator. So here this is simulating as an object which you need to sense, and it also simulates the various KPIs, like as if the object is moving at a certain velocity. And yeah, that is what is required for testing integrated sensing and communication. So this paired together with the base station emulator, which I showed you in the previous slides, the CMX500, then it's a perfect test bed for you to test ISAC in a lab on a test bench. Yeah. And yeah, artificial intelligence and machine learning. So this has been the talk today, and also tomorrow you will see many speakers talking about it. And from Rohde & Schwarz, we have all these tools, instrumentation, which can create data sets, meaningful data sets, which act as a data lake for companies like NVIDIA. We collaborate with NVIDIA, and they are working on enhancing each of these blocks which you see on the transceiver chain here as part of the communication system. Going forward, maybe once you have each of these blocks using well-trained models and artificial intelligence algorithms, so the whole communication system can be replaced with an auto encoder. So that is the vision. And maybe this will be a reality with 6G network architectures, where a fully trained, fully trained communication system can be just an autoencoder which reacts based on the data patterns and other KPIs. So this is where we are also collaborating with NVIDIA. This is also a test setup we have in Mobile World Congress. And here you can see we have already data where receivers are optimized, the channel status indication and the MIMO beamforming management. So these algorithms are being optimized based on the data sets which you can create with our instrumentation, the generator, analyzer, and the base station emulators and so on. Yeah. Here, the advantage is you have full control of all the parameters on the test bench and using the instrumentation. Yeah. You can change, you don't have to request the network operators, you don't need a end-to-end model network being set up in your labs, just a box which can simulate the entire network. And this will continue. We are just at the beginning, and we continue to provide our expertise in this area. And also a lot was talked about ubiquitous connectivity. There is a lot more to explore. For example, right now we have just started with NB-IoT based NTN. So this is maybe good for an emergency SMS, but what needs to be also considered is the communication, the ping-pong communication between terrestrial network to non-terrestrial network, and inter-satellite communications, and also how this interface between the terrestrial networks and non-terrestrial networks are going to evolve. And already we have, say for example, GEO for IoT applications, when we have LEO, then for latency aspects, lower latency applications, maybe LEO. And yeah, this is already work in progress. It's also a very interesting topic, and we have some press releases this week. If you search on Google, like say, we have worked together with Japanese satellite company, JSAT, and wherein we have our base station simulator, which acts as a terrestrial network, and that communicating to real satellites and also communicating to a UE in some other country. So this was realized very recently. We have a very good press release on that, and this is one of its kind unique test beds which you can explore. And also NTN is going to be really interesting for India case, because we have a lot of marine communications to monitor. We have a lot of ports which can be enhanced to be smart ports, and also with all these PLI schemes and production, India becoming a hub for production. So all these manufacturing plants, maybe in 5 years, 10 years down the line, can turn into smart manufacturing plants. So that is where even the networks, private networks and ubiquitous connectivity could play a big role. And lastly, reconfigurable intelligent surface. You know the theory behind. Here we are trying to modify the channel response so that often it had been in the communication channel, we change the transmitter characteristics based on the feedback we receive from the receiver. But now what if we can change the channel response itself? So that is where we have, say for example, passive RIS and also active RIS, where you can impinge a signal onto the surface, and then you can control where this beam has to be projected. Yeah. So in this direction, what would be important from a test and measurement perspective would be, say for example, there is a RIS device under test on the turntable, and you have an impinging angle where you inject or incident signal is a 5G signal, and then this has been reflected to a desired direction, and you want to see if this beam was the intended beam indeed. So for that testing, you need a chamber and then some rotating arms with antennas which can catch the beams, and this is a test and measurement setup where we have also some proof of concepts already in place to facilitate you to work on RIS topic. So this is a video. The crux of the test setup would be the generation, the feed antennas, or maybe the probes probes to capture, feed to transmit, and at different various angles of arrival. And here you have this unique product from Rohde & Schwarz, which is a chamber on wheels, which can come through any of these doors. You can push these chambers, and with which you can realize or test reconfigurable intelligent surfaces. So with that, I think we have covered some of these candidates and how to test that, and how Rohde & Schwarz is adding value to this ecosystem. And I would also like to emphasize and echo the same sentiments which was reflected by Mr. Pathak in the earlier sessions today morning, that we have to create. Now is the time to create ideas, and Rohde & Schwarz would play every role in making those ideas real, yeah, in your labs. So that is where we are working together with many universities and academia, research institutes, and there is a lot of money inflowing into these organizations to realize, to work on these future 6G candidates, and we are part of most of them, all of them in fact, and these are the alliances where Rohde & Schwarz is contributing. So with that, I come to the end of my presentation. So now is the time, that is what I want to say with this timeline picture. So now we have to start acting upon. So with that, I come to the end of my presentation. Thank you very much for attention. Thank you.
Okay, twist my arm. So you showed some experiments with RIS.
Yeah.
What kind of gains have you seen in your experiments using, let's say, 100 or 200 element RIS? What kind of SNR boost do you see?
Maybe I'm not supposed to reveal those data, but we do have a test setup, test bed, and I can privately answer your questions offline. Yeah. Thank you very much. Thank you.
So we thank Mahesh. So I'll request Ray to come on stage and give Mahesh a memento of appreciation. Yes. Thank you. Thank you, Mahesh. Thank you. Yeah, your pen drive is here. Yeah, and let's close this. Yeah. I think. Where is it? Yeah, here. I think you can take it out now. Yeah. Thank you very much. Yeah. So thank you, Mahesh. Very informative talk. So with that, we come to close of the first day. What better way to close the first day with talk and keynote address by the most celebrated telecom leader in India. So he doesn't deserve, I mean, he deserves a very big introduction, but I only have half a page, which probably is not enough to describe him. But I guess I'll stick to that for today. So he is none other than Professor Abhay Krandikar, who is currently the Secretary of Department of Science and Technology. Before joining DST in October 2023, he served as the Director IIT Kanpur from 2018 to 2023 on lien from IIT Bombay. He also served as Dean Faculty Affairs and Head of the Electrical Engineering Department at IIT Bombay. He spearheaded a national effort in setting up Telecom Standards Development Society of India, TSDSI, India's standards body for telecom with participation of all stakeholders. Professor Krandikar was the founding member and former chairman of TSDSI. He was also member part-time of Telecom Regulatory Authority of India, TRAI, from January 2018 to January 2021. Professor Krandikar has several patents issued and pending, contributions to IEEE, 3GPP standards, contributed chapters in books, a large number of papers in international journals and conferences to his credit. Professor Krandikar was awarded with IEEE's SA's Standards Medallion in December 2016 in New Jersey. His team also won Mozilla Open Innovation Challenge Prize in March 2017 for his work on rural broadband and digital empowerment in rural India. So with these words, I would like to invite Professor Karandikar on stage and say a few words. So thank you, sir, for taking out time for your extremely busy schedule and being here to address the audience. Thank you.
Thank you. So I'm busy doing nothing. So I think as my introduction, Dr. Saif said that I'm currently, so I think those of you who have come from US and other places, so just for them, I am Secretary to the Government of India in the Ministry of Science and Technology. So I asked Saif whether you want a secretary talk or whether you want a professor talk. So he said, no, secretary talk only will be okay for this. Now, as a secretary to the Government of India in the Ministry of Science and Technology, although as my background is in telecom, but I have spoken on climate change to food and water security. So I can speak on, therefore, any topic, for which the conference is there. And this sort of happens to be the conference in which I know something. So that's why I asked him whether, I can speak on 6G core networks or something. And he said, no, let it be like the same talk that I would go to a conference on food security. So let it be like that only. So first of all, let me welcome all the colleagues who have come from the US. I will just tell you about what the Government of India is doing. But let me just give you some broader perspective in the country. As you know that India has seen an exponential rise in the cellular mobile communication to the extent that cell phones are the primary telephones for most Indians and are also the primary broadband instrument, because we yet do not have like fiber to each and every home. And so therefore, I think, this is very critical. And if you look at the number of mobile broadband subscribers, in this July, the number was 900 plus million. So it's almost touching 1 billion mobile broadband subscriber. By broadband, I mean those who are having 4G and above. Now, even though, we have launched 5G, so this is another one characteristics of India, that even though we have launched 5G, we have still a very good network of 4G and 3G and even 2G. And some operators are still expanding their 4G networks while they are launching the 5G also. So this will be one of the largest heterogeneous multi-radio access technology network for a multi-rat HETNet. Same operator having 2G, 3G, 4G, 5G and Wi-Fi services providing that. And now perhaps some operators will also provide the broadcast services as well. And if you see the data volume for a smartphone, in India, the data volume for smartphone is about 30 GB per month. And this is the highest in the world. Because if you look at the US and the Europe, the average data volume per subscriber is in the range of 20 GB per month. And while in India it is 30 GB per month, resulting in about generating about 21 exabytes of data per month. So that is the volume that we have. And this is a scenario when not everyone has an access to 4G and 5G. There is not fiber to each and every home. And still, there is a large addressable market for mobile broadband, because still a significant percentage in the rural areas still do not have access to what we can call as a true mobile broadband. If I go with the definition of the Telecom Regulatory Authority of India's broadband definition, maybe we have a coverage of 90%. But if you want to call a true mobile broadband, we still have a large addressable market. And it is our estimate that if we really satisfy the broadband needs in the country, then by maybe in next 5 years, by 2030 or so, it is, at least our estimate that we may have to handle about 100 exabytes per month of data, which is, no Cisco Ericsson forecasts has done. And this we believe will be possible because the government of India has a lot of plans in reaching out the broadband on varieties of government-led initiatives, and also a very deeper penetration from the mobile operators. And this actually calls for some rethinking, and not just at the radio access, because most of them I know here are discussing about the radio aspect, improving the spectral efficiency, but a rethinking in the core networks is also needed, where very little work has been done. Because if you have to handle hundreds exabytes per month data in the core network, and if you have to handle this kind of subscribers, then there will be a significant signaling overheads that will come up. And in those signaling overheads itself, in the current core network design, in our opinion, will be actually the paradigm that needs to be entirely changed. So I think the sheer size and scale of the data that India offers, not just in the volume, but also in the diversity. In fact, this is also an analysis that we have, that a diversity of applications that currently India is having in terms of accessing the mobile internet is also much larger than anywhere in the world. And with just now what you heard in the talk on 6G, with immersive experience, integration of integrated sensing with other devices like high altitude platforms or UAVs and so on. And we believe that India, we will also have an integration of the mobile broadcast also, the broadcast TV. So broadcast TV will be one very, very important applications which has not, again, yet been explored that much. So India will present a network which will be a true test bed for testing the protocols and options for a truly multi-radio access technology HETNet. India will present a network where there will be a tremendous signaling overloads on the networks, not looked at anywhere. And it will present the kind of diversity of applications and the data sets which will be not available anywhere. And therefore, any work which will be driven by artificial intelligence and machine learnings in this will be really the real test beds where those algorithms can be tested and used. Because just as I mentioned, the sheer size and scale of the data, not just the traffic data, but also the diversity and also the signaling data, and all those data sets will be available for any AI system to analyze. Now, coupled with this, although most of the telecom networks is handled by our sister ministry, that is the Ministry of Communications and the Department of Telecom. In the Department of Science and Technology, we believe that the underlying bit pipe will just be a transport mechanism, and over that we have a tremendous opportunity for providing an overlay layer which can be roughly called as a cyber physical systems layer. And in this context, we have a large mission, national mission on cyber physical systems, where our ministry, our department has set up 25 mission hubs across the academic institutions in the country. And they are working on areas ranging from wireless communications to Internet of Things, to robotics, to unmanned vehicles, to the data science and artificial intelligence. So we have really a spectrum, which is not really the base stations or the transport mechanisms, but really the overlay layers, which will enable, the underlying technologies to be influenced by what kind of systems that, we are going to have as an overlay application layer. And in this context, we recently have undertaken, so this National Mission on Cyber Physical System was initiated in 2019. So in 2018-19, we now completed about 5 years. And we undertook a review of that mission. And in that now we will be consolidating some hubs. And in that activities, we see 4 major verticals emerging as a kind of important applications and use cases. One is like the resource and infrastructure. Another one is healthcare. Third one is agriculture, and fourth one is the environment. And these 4 verticals can really ride over a robust 6G networks, which could be a horizontal, pipe, and AI and machine learning, also another horizontal pipe, and of course the cyber security, another horizontal pipe. And this architecture we will now be implementing in our cyber physical mission in the remaining 3 years, where we would like to consolidate the activities of various hubs that were set up in our premier academic institutions. And in this context, therefore, we see the 6G transport layer to be an important mechanism where these 4 verticals will exist in order to drive the capacity of the 6G networks. And of course, the AI and machine learning can also act not only, to innovate on this transport network architectures, but also the upper 4 application layers that we consider important from the national priorities perspective. Another important mission that we have launched is the National Quantum Mission. Again, the government of India has put in about $1 billion approximately for the National Quantum Mission. And in that National Quantum Mission, we have 4 verticals. Quantum computing, quantum sensing are 2 important verticals. Quantum materials and devices is third. But the 4th important vertical, which has a direct bearing to this audience, is a vertical on quantum communication. And in the quantum communication, we have now set up a hub with IIT Madras and CDOT, and we will have several groups which are working under this hub to develop the technologies in the area of the quantum communications networks. And these are not just point-to-point link, but these are all multi-point-to-point links as well. And we see that an integration of the quantum communication networks with the 6G, providing an overall backend integrated homogeneous core, will actually be another opportunity for us to explore in that directions. Finally, I should also tell you that at the government, we are really committed to creating a very vibrant R&D ecosystem in the country. The government has recently established a National Research Foundation, which is called Anusandhan National Research Foundation, ANRF, along the lines very similar to National Science Foundation in the US. We are in fact going to have an MOU signed between NSF and ANRF for undertaking some large joint R&D programs. Of course, the Department of Science and Technology has done many calls with the NSF, but they have been of a smaller ticket items. At best, $200,000-$300,000. But this will be sort of hopefully will be the large research programs. We are now operationalizing the ANRF. It took about a year to put together, all aspects, because the erstwhile Science and Engineering Research Board now no longer exists. And we are now launching various programs of ANRF. We have recently launched for the early career grant and so on. Because Indian researchers have been struggling with R&D funding problems. So therefore, our priority is to launch those programs quickly. But I would like to say that we have a very strong international collaboration component in the ANRF, which we have not yet rolled out. Maybe in the coming few months, we will be rolling out. And there will be, of course, an opportunity for the researchers to collaborate on problems that are of mutual interest and also which we can address, some of the global challenges as well. And in that context, as I mentioned, that even in the ANRF, cyber physical systems, overall cyber physical systems, which includes not only just the communications infrastructure, but also, application verticals where we can make an important difference on the ground. Particularly in the context of what we call in India as a digital public infrastructure, which we overlay over a communication infrastructure that exists. So I think that integrated approach where a digital public infrastructure can be integrated with an underlying communications infrastructure of the size and scale that we are talking in India is extremely important from our point of view. Again, as I mentioned that I don't want to, talk more about, things which are not so aligned with the today's topic. Otherwise, I can give you a full perspective on what our ministry does. But one more important aspect and that we would like, the researchers who are working in the 6G to focus on the developing 6G, which is energy aware. And this is again extremely important in the Indian context. A lot of focus so far has been on improving the energy efficiency of the cell phones, making the batteries last longer and making the handset lightweight and so on. But little attention has been paid on the energy of the network nodes, which are in the transport networks or in the core networks. And again, as I mentioned, that the volume of the data that we are talking and plus the volume of the signaling loads that will come, the energy of those nodes will become extremely important because the energy that will be required in the processors to process simply such signaling loads will be extremely high. I mean, there are estimates and therefore very little work has been done to create an energy aware core networks, etc. And finally, of course, you can go very radical. You can even challenge the concept of the core network itself, because originally, if you see in the cellular mobile communications, the core network has come to anchor the mobility. But if you look at in the context like India, 90% of the cell phone users are generating almost 95% of the data while they are stationary, because this is our primary broadband instrument. Unlike if you are having fiber to the home, etc. And therefore a network which is optimized for stationary and fixed networks, but yet which will work very well when you are mobile, is real challenge that exists. And so although we are talking of a cellular mobile communication, it is mostly being used as a fixed networks as well, because of unless you go to a stage where you have a fiber to the home in each and every home, then in the home you can have a Wi-Fi, and then of course then you are using 4G or 5G only when you are stepping out of the home or the office, and then you are getting into the car, then mobility is the only issue. But it is not so, at least. It is very common in India to use your cell phone as a hotspot, even if you are accessing it, your laptop or the computer. So I think those are different dimensions that bring, the specific requirements. And as I mentioned, that integrating that with the overall cyber physical system and with the support from the AI and machine learnings offers really a rich opportunity for new innovations that can happen at various levels, right from the digital public infrastructure stack to the radio level. So that's all I had to say. I would once again like to congratulate SAF for organizing, putting together this interesting program and calling all the relevant stakeholders. I hope you will have a fruitful discussions in these couple of days wherever you are here. And from the government side, we will be happy to support any international collaborations which can emerge out of these discussions or otherwise as well through various mechanisms that exist. In the Department of Science and Technology, of course, we have an international cooperation division. By the way, all cooperations, international cooperations in science and technology, our ministry is a nodal ministry. We have actually a science counselor in Indian Embassy in Washington, D.C., which reports to DST, apart from science counselors in other countries also. And through them, we actually engage at the government level for all science and technology cooperations. So either through the Department of Science and Technology or through the National Research Foundations, we will be happy to work with any of you and partners. So thank you and wish you all the best.
Thank you, Professor Karandikar, for the talk. Thank you for giving us a glimpse into the government missions on addressing 6G capacity, into different schemes that you are coming up in maybe the next year. And thanks also for being a mentor to many of us and encouraging so many of us. Thank you. Yeah. So I will request Ray again to please come on stage and give a memento of appreciation to Professor Abhay Karandikar. So with that, we end today's session. So we'll have a photo shoot of the speakers today with Professor Abhay Karandikar in a short while. And then we have dinner for all delegates at 7 p.m. in the courtyard behind. So thank you.
No, actually, I'll tell you, I was just telling him, today morning I had a meeting in the Prime Minister's office, afternoon I had a meeting in the Cabinet Secretariat, and now I have to again go because there is some parliament, because this actually the parliament session is going on. I have to discuss with the minister after this ordinance. I was, if this was not there, I would have gone from the Cabinet Secretary to my home. I would have, and then would have gone.